Welcome to the CIPT exam preparation course, where we bridge the gap between technical system architecture and global privacy compliance requirements. This inaugural lesson establishes our pedagogical approach, the core structure of the certification, and how the curriculum aligns your engineering expertise with regulatory expectations. This course is an unofficial, independently produced study guide and is not affiliated with, endorsed by, or connected to the International Association of Privacy Professionals, IAPP. This content is for informational purposes only and does not constitute legal advice. Always consult a qualified legal professional regarding specific privacy compliance requirements and their application to your organizational needs. In this course, we treat privacy as a first-class engineering concern rather than a simple legal checkbox. You will learn to internalize the CIPT mindset, which demands that data protection be embedded directly into the software development lifecycle, network topology, and database design. Whether you come from a background in DevOps, security architecture, or software development, the objective here is to transform your existing technical skills into a robust framework for privacy compliance. We are not just preparing you to pass an examination. We are equipping you to build systems that respect human rights by design and by default. To succeed, you must understand that the IAPP CIPT exam focuses on the technical implementation of privacy principles. The evaluation consists of 70 multiple-choice questions designed to test your ability to apply abstract privacy concepts to concrete technical scenarios. We need to be clear about the scoring. There is no single golden ticket for every technical problem, as the correct response almost always depends on the specific context of the data, the jurisdiction, and the architecture in play. By the end of this program, you will possess a structured mental model to evaluate these variables systematically and arrive at the most compliant architectural decision. We will systematically navigate the entire body of knowledge, starting with privacy engineering fundamentals and moving through data mapping, risk assessment, and specific privacy-enhancing technologies. You will see how concepts like data minimization, pseudonymization, and differential privacy interact with practical concerns like identity management, auditing, and incident response. We also dedicate significant time to emerging technological domains, such as artificial intelligence, the Internet of Things, and cloud-native environments to ensure you are future-proofed. Most importantly, we will connect these high-level technologies to operational realities, ensuring that your theoretical knowledge translates into actionable DevSecOps workflows. As you build your study roadmap, remember that the most effective way to learn this material is by mapping it to your current professional environment. Think of the data lifecycle within your own organization. How is it collected? Where is it stored? How is it protected? And eventually, how is it destroyed or archived? By viewing the course content through the lens of your own daily responsibilities, the often abstract requirements of regulations like the GDPR or CCPA transition into manageable technical debt or configuration items. This empirical approach is essential because the CIPT exam expects you to demonstrate a practical, practitioner-level understanding of how technical controls mitigate privacy risks effectively at scale. In upcoming modules, we will dive deep into the architecture of privacy and look at how technology can serve as a catalyst for trust. I look forward to guiding you through this material as we refine your technical expertise for the CIPT certification. See you in the next lesson. Welcome to our new chapter, where we will define the technical role of the privacy professional and explore how to bridge the gap between compliance and implementation. We are here to transform how you view the intersection of engineering and privacy within a modern corporate structure. When we talk about the role of a privacy technologist, we are not simply discussing a policy advisor who sits in a siloed department. Instead, we are looking at a specialized practitioner who functions as a translator between the rigid constraints of data protection laws and the fluid agility of contemporary software engineering. In most organizations, the legal team expresses requirements in abstract, high-level mandates, such as the obligation to ensure data integrity or the necessity of providing users with portability rights. The privacy technologist must ingest these mandates and decompose them into actionable, technical, functional specifications that developers can actually implement in their daily work. This process requires a deep understanding of not just the regulatory landscape, but also the technology stack itself, including everything from microservices architecture to cloud-native database configurations. Without this translation layer, legal requirements often remain unimplemented or become mere documentation that fails to mirror the reality of the production system. To effectively influence a complex corporate environment, you must establish collaborative bridges with several key stakeholders who often speak very different professional languages. Your daily activities will involve frequent synchronization with data protection officers who focus on the regulatory compliance posture, and chief information security officers who are primarily concerned with the CIA triad of confidentiality, integrity, and availability. Furthermore, your involvement extends to business line managers who prioritize rapid feature delivery and market velocity over bureaucratic bottlenecks. You must position yourself as a technical asset rather than a project inhibitor by demonstrating that privacy by design actually leads to cleaner code and more robust technical architecture. By facilitating these interactions, you ensure that the privacy requirements are baked into the system during the design phase rather than being treated as a burdensome patch at the end of the development cycle. Strategic alignment within the organization requires the creation of multi-tiered technology governance frameworks that turn subjective policies into verifiable metrics. A governance framework is essentially a structured approach that dictates how an organization manages its data, defines who possesses the authority to make changes, and specifies the necessary documentation for audits. As a technologist, you will define the standards for how software development teams handle data, which might include specific requirements for logging, access control, and storage retention patterns in a cloud database. You need to develop internal verification systems that allow you to programmatically or heuristically gauge how well a specific system aligns with your established organization-wide privacy standards. This might involve creating automated security tests that trigger when a deployment pipeline encounters a violation of your privacy policy, such as an attempt to log unencrypted personal identifiers. The documentation aspect of this role is often misunderstood as merely fulfilling a bureaucratic checklist, but it is actually the bedrock of institutional memory for data processing. You must ensure that every architectural decision involving personal data is documented in a way that is accessible to legal counsel while simultaneously serving as a technical reference for your peers. This involves maintaining a clear mapping of data flows and ensuring that your technical documentation evolves in lockstep with the software itself. When regulatory bodies eventually ask for proof of compliance, your capacity to provide a clear, technical audit trail is exactly what shields the organization from liability. By treating documentation as a living part of the system's architecture, you transform what could be an agonizing audit preparation period into a routine verification of your existing engineering health. Achieving maturity in this role necessitates that you move beyond static compliance and toward a model of continuous, privacy-aware engineering. You are not just checking boxes. You are auditing systems, verifying configurations, and iterating on the privacy-enhancing controls that protect user data throughout its entire lifecycle. This requires an iterative mindset where you continuously analyze the threat landscape alongside the development team, ensuring that any new code pushed to production does not inadvertently break the privacy safeguards previously established. Through this systematic approach, you become the essential link that maintains the integrity of the data ecosystem while enabling the business to scale its operations responsibly. See you in the next lecture. Welcome to our discussion on design principles, where we will translate abstract privacy concepts into actionable architectural requirements. We will specifically cover how to integrate privacy by design and default into your engineering lifecycle. When we talk about privacy by design, we are often guilty of treating it as a philosophical abstraction rather than a technical specification. In practice, however, these principles must manifest as concrete constraints within your code base and system architecture. The core of this methodology lies in moving from reactive compliance to proactive embedding, where privacy is not an add-on, but a fundamental property of the system. Think about how you would implement proactive controls within your database schema or your API layer to ensure that data minimization is enforced at the point of capture. If your system architecturally requires PII to function, you have already failed the design test regardless of your external policy documents. We need to focus on zero-sum alternatives, meaning we look for ways to gain user utility without sacrificing privacy rather than settling for a trade-off where one must suffer at the expense of the other. Achieving end-to-end lifecycle encryption requires us to look beyond simple TLS connections and examine how data rests in persistent storage and moves through inter-service communication. You must define clear boundaries where data is encrypted at the application level before it ever hits an ingestion point or a database driver. This ensures that even with elevated administrative access, the raw data remains opaque to those who do not hold specific keys within the memory space of the processing service. Consider the challenge of maintaining operational visibility while keeping data encrypted. This necessitates patterns like homomorphic encryption or secure multi-party computation in specific high-sensitivity use cases. By hardening the data structures themselves, rather than relying solely on perimeter security or identity-based access control, you reduce the blast radius should an underlying component be compromised. It is an exercise in minimizing the trust surface of your infrastructure's individual nodes. System defaults are perhaps the most powerful implementable lever an engineer has to influence user privacy outcomes. When we design for privacy by default, we are choosing the most restrictive configuration as the baseline state, requiring explicit, granular action from the user to elevate their exposure. This is fundamentally different from a system that asks a user to opt out via a complex settings menu, which is effectively a dark pattern that relies on configuration apathy. In an enterprise environment, this means your API should reject any request that does not include necessary scoping parameters for data access. By enforcing these constraints at the baseline application layer, you ensure that the system behaves predictably and securely without relying on the manual intervention of developers who might otherwise bypass privacy controls for the sake of convenience. It puts the control architecture in the hands of the system designer through declarative policies rather than procedural code. Algorithmic bias is another critical dimension of system design that often escapes traditional security reviews. To prevent encoded biases, you must establish technical parameters that explicitly strip extraneous data points that are not strictly necessary for the intended function of the algorithm. If your processing logic is influenced by high-variance identifiers that correlate strongly with protected classes, you are building in systemic risk that will be difficult to remediate later. Maintain operational visibility by instrumenting your pipelines to audit the influence of specific input features on the output of your models or processing rules. If the system cannot justify the use of a specific set of features based on the primary system function, those features should be discarded during the data ingestion pipeline. This is a technical validation step that acts as a guardrail against both privacy violations and unfair processing outcomes. By grounding these frameworks in technical realities, you ensure that privacy remains a constant constraint throughout the development lifecycle. I look forward to discussing how these principles apply to the system lifecycle in our next meeting. Welcome back. Today, we are exploring system lifecycles as a core component of embedding privacy directly into the technical fabric of an organization. In this lesson, we will examine how to integrate privacy workflows into your development processes to ensure compliance and robust data protection. Historically, the waterfall methodology served as the standard for software development, characterized by rigid, sequential phases that often relegated security and privacy reviews to the final stages of the process. In such a model, a privacy incident discovered during the testing or deployment phase often proved prohibitively expensive to remediate, leading to shortcuts or delayed launches. Modern Agile frameworks and DevOps architectures have fundamentally shifted this paradigm by encouraging iterative development, smaller releases, and crucially, the shifting left of security and privacy concerns. By integrating privacy checkpoints into the earliest stages of the SDLC, we move from reactive compliance toward a proactive, privacy by design posture. This transition necessitates an understanding that privacy is not a static gate at the end, but a continuous series of validations occurring throughout the development lifecycle. In current cloud-native environments, the adoption of continuous integration and continuous delivery, or CI/CD pipelines, has transformed how we deploy software. These pipelines allow teams to automate quality assurance, but they also offer a unique opportunity to automate privacy and security governance without disrupting developer velocity. When we look at automated testing, we must focus on tools like static application security testing, or SAST. which examines source code for vulnerabilities or potential data leaks before the code is even compiled. Simultaneously, dynamic application security testing, or DAST, tools operate on the running application, identifying security flaws by simulating real-world attacks while the system is in an active state. Integrating these tools into the CI/CD pipeline ensures that every commit is essentially audited against a baseline of privacy requirements, preventing the accidental exposure of sensitive information that might otherwise drift into production. Establishing mandatory gates within your pipeline is a critical tactical methodology for maintaining the integrity of the data environment. A gate is essentially a hard stop in the automated process where the code must pass specific privacy and security validations before it can proceed to the next stage of deployment. For instance, you might configure your pipeline to block any build that includes high-risk dependencies, which are often the source of supply chain attacks. Validating the integrity of third-party libraries is equally important, as compromised open-source packages represent a significant, often overlooked, vector for data exfiltration. Furthermore, by creating and maintaining reproducible privacy test scripts, you ensure that every environment, from development to staging, can be verified using the same consistent set of standards, thereby mitigating inconsistencies that lead to vulnerabilities. Finally, we must account for the structural stability of the system by building comprehensive automated regression tests. In a rapidly evolving codebase, a feature added today might inadvertently break a privacy control implemented months ago, and regression tests are the safety net that catches these unwanted changes. These tests should specifically target data flow paths to confirm that even after updates, the system continues to enforce internal privacy policies, such as data residency constraints or specific obfuscation requirements. When an automated test fails, it provides immediate feedback to the engineer, allowing for rapid correction well before the code ever interacts with production data. This structured approach effectively minimizes the surface area for privacy regressions and ensures that the system remains resilient against technical drift as it scales. I will see you in the next lecture. Welcome back. In this lesson, we will focus on the practical application of privacy frameworks within engineering environments. When we talk about privacy frameworks like NIST or ISO IEC 27701, it is common to view them as purely administrative documents meant for auditors or high-level management. However, as privacy engineers, we must view these frameworks as sets of codified technical requirements that translate directly into system configurations. If an ISO standard mandates the protection of personally identifiable information during transmission, your engineering task is not just to acknowledge the policy, but to configure the specific TLS version and cipher suites that enforce that protection. We essentially map the abstract language of risk registers into concrete firewall rules, database encryption schemas, and identity access control lists. This transition from policy to parameter is where privacy engineering actually happens. By standardizing these mappings, we allow the security team to evaluate the system against a known, measurable baseline rather than an ambiguous set of expectations. The Privacy Management Reference Model, or PMRM, provides a structural way to visualize the flow of data across a system, which is essential for applying these frameworks effectively. Instead of treating privacy as a fuzzy concept, the PMRM forces us to define the specific service, the data subject, and the technical control at each stage of a lifecycle. For example, if you are implementing an automated erasure policy, you need to identify the intersection between the data store and the user request interface. This intersection is your control point. Within that control point, you establish the KPIs, such as the latency between a deletion request and the propagation of that removal signal to secondary replicas. Without this granularity, frameworks remain document-based illusions that fail to prevent actual data exposure. Mapping controls across multiple standards can feel overwhelming if you try to manage them manually, but it is necessary for architectural flexibility. Most modern enterprises operate in a heterogeneous environment where regulatory requirements from different jurisdictions overlap significantly. By creating a unified control matrix, you can verify that a single technical implementation, such as enforcing multi-factor authentication, simultaneously satisfies the access constraints of the NIST privacy framework and the security requirements of ISO IEC 27701. This approach minimizes administrative overhead because you are effectively auditing a single system configuration against multiple business objectives. When an auditor asks for evidence of compliance, you provide logs showing consistent enforcement of these parameters across your network. This is the goal of operationalizing privacy, to turn regulatory pressure into a predictable, automated, and observable system state. When looking at log configurations, we must ensure that they meet privacy requirements without becoming a liability. Enabling full logging of raw request parameters might provide excellent debugging data, but it likely violates the principle of data minimization inherent in most privacy frameworks. Therefore, your technical security design must include a pipeline to strip or redact sensitive fields before those logs reach long-term storage or analysis platforms. This is an operational parameter that turns the privacy by design principle into a concrete instruction for a log aggregator. Similarly, when configuring transmission protocols, we move beyond simply stating that encryption is used. We define the specific, acceptable key lengths and key rotation schedules that provide the necessary assurance for the sensitivity of the data being processed. Establishing these operational baselines simplifies the lifecycle of any technology platform because it creates a standard template for new deployments. Every time you stand up a new system, you apply the same internal standard for identity verification, data encryption, and access auditing. This reduces the cognitive load on engineering teams, as they no longer have to guess how to interpret data protection requirements for every individual project. Automating the verification of these controls is the next maturity step, where scripts or configuration management tools periodically scan your infrastructure to detect drift from the baseline. If an encryption setting is disabled, the system alerts you immediately, facilitating a faster incident response. This is how you shift from reactive compliance to proactive privacy architecture. I hope this helps you understand the operational reality of frameworks. We will continue from here in the next lecture. Hello. Let us examine the systematic approach to identifying privacy vulnerabilities through the lens of threat modeling. Threat modeling is a structured process for identifying and mitigating potential security and privacy risks within a system architecture. While many software engineers are familiar with security-centric frameworks, applying these techniques to privacy requires a distinct shift in perspective. Instead of solely focusing on unauthorized access or system uptime, our objective is to protect data subjects and ensure technical compliance with privacy by design requirements. By analyzing data flow diagrams, we can trace how information moves, where it is stored, and who possesses the technical capability to view or process it. This systematic analysis allows us to uncover architectural flaws that could later manifest as significant privacy breaches. We move beyond simple checklists to examine the structural interactions between components, services, and external interfaces. A fundamental framework for this endeavor is Lindawn, which specifically addresses privacy threats in software development. This methodology categorizes threats into 7 distinct buckets: linkability, identifiability, non-repudiation, detectability, disclosure, unawareness, and non-compliance. Linkability concerns occur when an attacker can correlate two disconnected items of data to infer something about a user. Identifiability involves the ability to associate a specific dataset with a natural person, while non-repudiation issues arise when a user can deny an action they actually performed, often a problem in logging systems. Detectability refers to the ability to distinguish whether a specific user is involved in an event or interaction. Disclosure is the straightforward, unauthorized revelation of private data, often due to improper access controls. Unawareness captures the risk that users are engaging with a system without fully realizing what data is being collected or how it is being processed. Finally, non-compliance reflects the structural failure to meet legal obligations or established organizational policies. To complement Lindawn, we look toward the MITRE Panoptic methodology. This framework emphasizes the identification of technical privacy risks within complex, distributed environments such as cloud-native architectures. Unlike traditional security modeling, it forces us to evaluate the privacy implications of API telemetry, metadata collection, and the cascading effects of third-party service dependencies. When we perform a deep dive into an application, we start by decomposing the system into its core functional components, and mapping the precise data flows between them. We ask ourselves where data is transformed, where it enters unencrypted zones, and where excessive metadata might allow for inadvertent re-identification of individuals. By labeling each node and flow within our diagram, we create a technical baseline that makes latent vulnerabilities visible. This process transforms abstract privacy concerns into concrete engineering tasks that can be tracked in a standard development backlog. Once we have mapped these flows, we must address the difficult task of quantifying technical risk. It is rarely sufficient to simply report that a vulnerability exists. Stakeholders often require a standardized metric to prioritize remediation efforts. Industry standard engineering scorecards allow us to categorize threats based on their severity, likelihood, and potential privacy impact on the data subject. We evaluate each identified flaw against the baseline of organizational data handling policies and regulatory thresholds. A high-risk vulnerability, such as an insecure API exposing sensitive personal identifiers in plain text, must be ranked appropriately against more architectural concerns like excessive data retention. By maintaining a consistent, repeatable framework, we ensure that every application in the enterprise, whether legacy or cloud native, is evaluated against the same privacy rigor. This consistency is the hallmark of a mature privacy by design operation. Moving from theory to institutional practice requires building a repeatable framework that teams can naturally integrate into their workflows. We want to avoid static documents that sit on a shelf. Instead, we aim for living models that evolve alongside the codebase. Whenever a security architect proposes a new service integration or a data migration, the team should trigger a lightning round threat model session using these established Lin-Dun categories. During this phase, we look specifically for shadow data flows and hidden leaks that often plague third-party integrations. Privilege escalation in a privacy context refers not just to gaining administrative access, but to the unauthorized expansion of the scope of data access permitted to a specific service or role. By embedding these checks into our design phase, we catch structural flaws long before they reach production, saving considerable resources and protecting individual privacy rights. See you in the next lecture. Welcome to this session on organizational context, where we bridge the gap between technical privacy design and broad business objectives. We will explore how to integrate privacy metrics into your company's institutional framework. In this chapter, we explore how to align your technical privacy infrastructure with the grander strategy of the corporation. If you have ever felt that your privacy engineering efforts are operating in a silo, this is the material that will finally help you speak the language of the boardroom. By mastering the integration of privacy metrics into your existing key performance indicators, you will be able to demonstrate tangible security and compliance value to stakeholders who might otherwise prioritize speed over safety. You will learn to navigate the complexities of procurement and enterprise architecture, transforming privacy from a perceived hurdle into a competitive business advantage. We will cover the practical realities of organizational pushback, the technical debt that complicates compliance, and the precise methods for calculating the return on investment for your technological deployments. If you want to move beyond being a technical resource and start acting as a strategic partner within your organization, this chapter is designed specifically for you. Aligning information technology strategies with operational business objectives requires a fundamental shift in how we perceive privacy engineering. It is not merely about selecting the right encryption algorithm or configuring a firewall, but ensuring that these choices support the overarching goals of the enterprise. When you design a database architecture, you must consider whether the underlying data structure supports the divergent legal standards found across different jurisdictions. A storage strategy that works perfectly for domestic data may introduce significant legal friction if the expansion plan includes operations in markets with stringent data residency requirements. By embedding privacy directly into your hardware procurement policies and enterprise application roadmaps, you effectively preempt the expensive retrofitting that occurs when privacy is treated as an afterthought. This proactive approach relies on clear communication, where you articulate technical risks in terms of business impact, such as potential downtime, loss of consumer trust, or regulatory sanctions. Integrating privacy metrics into existing corporate key performance indicators is a reliable way to make privacy visible to the executive suite. Most organizations track uptime, latency, and throughput, yet privacy performance is frequently absent from these performance reports. If you define a privacy metric as the number of data subject access requests fulfilled within the statutory window, you have provided a concrete measure that business leaders understand as a service-level agreement. Similarly, demonstrating the impact of privacy-enhancing technologies on reducing data incident response costs creates a compelling financial narrative. These metrics must be quantifiable and consistently reported, allowing management to evaluate privacy posture with the same rigor they apply to sales or operational efficiency. When you manage to align these technical indicators with institutional incentives, you align your privacy objectives with the motivation of the department heads who manage the budgets and the technical roadmaps. Managing multi-jurisdictional compliance architectures represents perhaps the most significant challenge for modern enterprise architects. When your database structures must concurrently support distinct international standards, you are faced with a complex design problem that standard centralized systems often fail to address. You might consider a federated database approach, where data remains within its region of origin while providing standardized interfaces for global reporting. This architecture allows you to maintain compliance with local laws, while meeting executive requirements for unified data access. It requires careful management of schema design to ensure that field-level security can be enacted based on the jurisdiction of the user or the origin of the record. The technical debt inherent in legacy systems often complicates this, as older applications may not support the granular tagging required for such architecture. Addressing technical debt and internal resistance to privacy controls requires a nuanced social and technical approach. It is common to encounter pushback when a new control, such as a mandatory data masking layer, threatens to increase latency in an already stressed production system. To mitigate this, you must treat privacy controls as professional software products that require iteration and performance tuning, just like any other feature. Instead of forcing a rigid binary secure or insecure choice, propose a phased deployment that maps out risk reductions against operational impacts. Articulately explaining how these controls protect the business from litigation or brand damage often lowers the resistance from technical teams focused solely on feature velocity. When you quantify the cost of a potential breach versus the cost of implementation, you provide the context needed for non-technical leadership to make informed decisions. Calculating the return on investment for technological privacy deployments involves looking beyond simple cost avoidance. You should view these investments through the lens of business continuity, process optimization, and the reduction of audit preparation hours. For example, automating the data inventory process not only fulfills a legal obligation, but also provides the business with a better understanding of its own data assets, which can lead to improved data quality and reduced storage costs. When you build the business case for a new privacy orchestration tool, focus on these side benefits alongside the primary compliance goal. Framing your work as an infrastructure improvement that increases the agility of the firm makes the investment much easier to defend during budget cycles. This level of professional communication ensures that technical privacy risks are viewed as central, high-priority variables in the overall health of the enterprise. I will see you in the next lecture. Welcome back. This chapter focuses on the mechanics of creating and maintaining a data inventory within modern, complex enterprise architectures. Building a functional data inventory in a distributed environment requires moving beyond static spreadsheets toward dynamic, automated discovery mechanisms. When systems scale, manual documentation becomes obsolete almost the moment it is finished, meaning you must integrate discovery agents directly into the infrastructure. These agents operate by scanning network segments to identify active endpoints, listening for traffic patterns, and querying configuration management databases to catalog new assets as they spin up. Think of a database crawling tool as a specialized bot that periodically inspects schema definitions and table metadata to ensure that what we think is in the repository matches the actual structure. This continuous monitoring approach allows an organization to maintain visibility over shadow IT assets that developers might deploy without following formal procurement processes. By automating the capture of these data points, we transform an exhausting administrative chore into a background service that runs reliably as part of the operational stack. Once you have identified the locations of your data, you must document the actual data lineage to understand how information travels between services. This involves mapping precise ingress points, such as an API gateway receiving a customer request, and egress points, where that data might flow to a third-party analytics provider or a secondary region. You need to leverage code monitoring software that hooks into your CI/CD pipelines to track data movement at the application layer, which is often where the most critical transformations occur. When an application changes, the inventory should automatically update because it is linked to the deployment process itself, reflecting current reality rather than historical design documents. This technical discipline ensures that your map represents the actual state of cross-border transmissions, which is vital for maintaining compliance with regional data residency requirements in a globalized cloud architecture. To make this data useful for privacy engineering, we must adopt structural formats that allow for complex query capabilities across the entire metadata catalog. I prefer using unified graph database configurations because they excel at tracing the intricate relationships between entities, users, services, and data elements, which are difficult to model in traditional relational tables. Within this structure, you should implement robust metadata tagging schemas that categorize data not just by type, but by sensitivity level, lifecycle stage, and ownership. For instance, tagging a data field with the origin application, the PII category, and the specific retention policy allows for programmatic enforcement of privacy rules across disparate databases. When you treat the data inventory as a dynamic graph, you can instantly visualize the impact of altering a single upstream service on all downstream data consumers. This is the difference between a list of files and a living, breathing model of your enterprise's information ecosystem. Maintaining this inventory requires a shift in mindset from periodic assessment to a state of perpetual awareness. By baking discovery into the architecture through agents and schema cataloging techniques, you ensure that every part of the network architecture reports its own telemetry to your central graph database. If a microservice undergoes a schema change that introduces a new data flow, the inventory tool should detect the discrepancy immediately and flag it for privacy review. This is how you build a resilient privacy program that can scale infinitely, even when the underlying application architecture changes daily. Accurate, automated, and deep integrated inventories are the foundation of any sophisticated privacy engineering practice, allowing you to prove your compliance through empirical data rather than speculative checklists. As you implement these tools, you will find that the technical depth of your visibility acts as the strongest barrier against accidental data exposure and non-compliant processing practices. I will see you in the next lecture. Welcome back to our exploration of data privacy. Today, we turn our attention to the architectural necessity of classifying data within complex, modern ecosystems. Data classification is not merely an administrative exercise in labeling spreadsheets. It is the foundational requirement for any automated privacy control. If we cannot programmatically distinguish what constitutes personal data from harmless system noise, we cannot enforce policies like retention, encryption, or access restriction at scale. When dealing with structured relational databases, the schema itself often provides a natural taxonomy, allowing us to build precise classifiers based on data types and column definitions. However, the true challenge arises when we confront unstructured data lakes, where petabytes of flat files, server logs, and raw binary artifacts reside without inherent structural metadata. In these environments, we must implement a layered detection strategy that assumes entropy is the default state of the storage layer. To master this, we rely on a combination of regular expression engines for consistent patterns, such as social security numbers or credit card formats, and machine learning models capable of inferring context in longer textual strings. Configuring these detection mechanisms requires a deep understanding of natural language processing to differentiate between a generic numeric sequence and actual personally identifiable information. Standard regular expressions are excellent for high precision, low recall tasks, yet they frequently fail in unstructured environments due to the presence of false positives and the lack of contextual awareness. By integrating NLP, we can analyze the grammatical structure surrounding potential PII, allowing our classification engines to distinguish between a customer's name used in a purchase record versus a similar syntax appearing in a technical error log. For unstructured logs or raw network traffic, we often deploy weighted scoring systems where a regex match contributes a certain probability weight, which is then refined by a machine learning classifier. This pipeline, when properly tuned, effectively filters the massive signal-to-noise ratio inherent in contemporary distributed storage systems, ensuring that only data requiring protective controls is escalated to our security infrastructure. Once the classification engine identifies PII within a data object, the next operational hurdle involves applying granular metadata tags that machines can parse in real time. This is often achieved by embedding security attributes directly into the metadata layer of the file system, or by utilizing sidecar configuration files that map specific data objects to their corresponding protection policies. If a system identifies a specific flat file as containing sensitive data, it should automatically trigger a write-to-disk operation that includes restrictive metadata headers. Within relational databases, we can use stored procedures or triggers to update classification flags in system tables whenever new records are ingested. This architecture transforms the classification layer into an active policy enforcement point rather than a passive report. Think of this as defining a contract between your identification logic and your storage layer, where the classification acts as the trigger for automated system behavior. To make these automated systems truly resilient, we must treat our classification logic as code, subjected to the same rigorous testing and version control as any other component of our application. Writing classification code necessitates a modular approach where specific patterns are abstracted into reusable functions that represent our organizational definition of sensitive data. If we discover that our regex engine is triggering too many alerts on non-sensitive log entries, we should be able to update our pattern definitions and redeploy them across our infrastructure without manual intervention. This level of automation allows for the creation of policy-based storage restrictions. For instance, any object classified with a high privacy sensitivity tag is immediately moved to an isolated, encrypted storage bucket by the underlying orchestration service. This lifecycle approach ensures that our privacy posture evolves alongside the data rather than lagging behind it. The goal is to move from manual, compliance-driven discovery toward an integrated, automated privacy by design framework that operates at the speed of our software delivery pipelines. We'll see you in the next lecture. Welcome back. In this lecture, we are going to explore the mechanics of conducting privacy impact assessments and data protection impact assessments through a technical lens. When we talk about impact assessments in the context of engineering, we must move beyond checkbox compliance and focus on the technical reality of data exposure. A privacy impact assessment, or PIA, serves as a systematic evaluation of a system architecture to identify how PII flows through various endpoints and processing layers. To perform this effectively, you need to dissect the underlying network design and look for vulnerabilities in database replication configurations where data might inadvertently be mirrored to insecure environments. Consider an encryption key path. If the keys reside on the same logical server as the encrypted data store, your technical assessment must reflect that reduced risk mitigation. Similarly, your evaluation needs to inspect the data retention enforcement scripts to confirm they trigger at the defined lifecycle end, rather than merely assuming the cron job is functional. This level of granular inspection ensures that the resulting risk scores are based on actual technical behavior rather than abstract policy claims. By documenting these design choices rigorously, you build a trail of evidence that substantiates your privacy posture to non-technical stakeholders and regulators alike. Moving into the formal Data Protection Impact Assessment, or DPIA, we transition toward calculating definitive risk scores based on a combination of probability and potential harm. You should approach this by quantifying the likelihood of an unauthorized access event against the severity of the damage that would occur if the data were accessed. For instance, if you were analyzing an API telemetry flow, calculate the probability of interception by assessing the transport layer security standards in place. If the potential harm includes large-scale identity theft or permanent loss of data integrity, the risk score must reflect the highest weighted value, triggering a requirement for compensatory controls. You are essentially conducting a form of quantitative threat modeling where the impact is a derived variable based on the technical complexity of the system. This requires that you verify the efficacy of your mitigation strategies by rerunning your assessment after applying security patches or architectural changes. The goal is to establish a delta that demonstrates how your engineering changes have successfully reduced the residual risk to an acceptable tolerance level. Engineers should aim to build reproducible evaluation templates that can be integrated directly into automated issue tracking systems like Jira or similar platforms. Instead of treating these assessments as static documents that sit on a shelf, integrate them into your continuous integration and deployment pipelines as a formal gate. When a developer submits a pull request that alters how PII is sharded or encrypted, the issue tracking system should automatically prompt a reevaluation of the relevant impact assessment categories. This allows you to log leftover system vulnerabilities in a way that is visible to the entire product team, ensuring that technical debt related to privacy is managed alongside functional requirements. You should define your compliance targets clearly within these templates so that any deviation is flagged immediately by your automated tooling. By mapping your impact assessment directly to engineering tasks, you make privacy a shared responsibility that is objectively measurable through the lens of technical operations. This methodology ensures that your privacy documentation remains a living, accurate reflection of the production environment. See you in the next lecture. Welcome back to our exploration of privacy engineering. Today, we turn our attention toward identifying the systemic risks inherent in distributed architecture. In any complex distributed environment, we are not just managing data in isolation, but managing the pathways through which that data flows. A common structural risk involves data bloat, where systems accumulate information well beyond the scope of their original purpose under the guise of future utility. When databases grow unchecked, they act as high-value targets for attackers, and this mass storage often lacks the granular controls required by modern privacy regulations. We must treat every storage bucket as a potential liability, especially when developers implement secondary processing pipelines that siphon data into analytics platforms without implementing corresponding privacy safeguards. These pipelines often bypass the primary security controls, creating shadow data stores that are invisible to the organization's central governance logs. If we do not actively audit these secondary paths, we effectively lose accountability for the data's lifecycle. Excessive logging is another systemic hazard that often goes unnoticed until a compromise occurs. Architects often configure debug levels to capture verbose outputs, inadvertently including personally identifiable information in logs that are then ingested into centralized aggregation systems. Once this information enters a logging stack, it is rarely subjected to the same retention or deletion policies as the primary database, leading to long-term storage of sensitive, unencrypted credentials or user identifiers. Furthermore, overprivileged API integrations exacerbate this issue by granting secondary microservices wide-reaching read access to monolithic data structures. In a well-designed system, an analytics service should never require the same permission set as the transactional core. By enforcing strict structural segregation, we ensure that an exploit in an external-facing dashboard does not necessarily provide a vector for lateral movement into our sensitive user record databases. Unauthorized data recombination represents perhaps the most sophisticated risk in distributed systems. When individual data points are harmless on their own, the aggregation of these points across multiple services can create a high-fidelity profile of an individual, which inherently changes the risk profile of the stored data. We see this often in architectures where different teams utilize shared message buses, where various streams of events might be joined by a downstream process to derive new insights. If our schema management is loose, unexpected modifications to data structures can inadvertently expose hidden relationships that were previously isolated. We need to implement automated auditing mechanisms that go beyond simple connectivity checks to actually validate schema integrity and flag unauthorized join operations in real time. This requirement for automated auditing of broken access paths is not just a best practice, but a fundamental requirement to prevent data leakage during routine system updates. Applying structural segregation requires a shift in how we think about component boundaries. We must define clear trust domains, where core operational components are strictly quarantined from secondary analysis and reporting architectures. This involves moving away from shared database models towards service-oriented architectures where data access is mediated through contracts rather than direct table access. When we treat every data interaction as an explicit API call, we can maintain clear audit logs that detail precisely what information is crossing domain boundaries. By standardizing these patterns, we reduce the likelihood of accidental mass data exposure and force developers to consider the sensitivity of the data they are requesting. This creates a defensive posture that remains robust, even when individual components within the broader distributed environment are compromised. See you in our next session. Welcome back. In this session, we turn our attention to the discipline of data lineage, where we define the exact path a piece of information travels from its ingestion point to its final consumption within a complex architecture. Data lineage creates a verifiable trail of how data enters your ecosystem, how it is transformed, and where it eventually resides. If you imagine a data point as a physical object, lineage is the manifest that remains attached to it, detailing every handoff, storage location, and modification process. In a modern multi-cloud streaming environment, this is rarely linear. You might ingest raw user information from a mobile application into a Kafka cluster, perform real-time windowed aggregations, and then persist the resulting insights into a data lake for long-term analytics. Without proper documentation of this path, you lose the ability to prove that you are adhering to the original consent parameters established at the moment of collection. Engineering teams should view lineage not just as a compliance requirement, but as a technical necessity for maintaining the integrity of the information lifecycle. To establish robust tracking, we must implement metadata tags at every transition point in the ETL pipeline. This involves configuring tools to log not just the data value itself, but also the context of the transformation function applied to that value. When your service consumes a message from a Kafka topic, the header of that message should ideally carry metadata describing the source and the sensitivity level. If you perform a transformation, such as hashing an email address to create a user identifier, your lineage metadata must explicitly record that the downstream asset was derived from that specific source data. Using deterministic hashing schemas here is essential, as it allows you to verify the origin of a dataset later without needing to hold the sensitive raw values in your audit logs. This creates an immutable chain of custody that is accessible during internal security reviews or regulatory inquiries. One of the common points of failure in complex systems is the mismatch between schema histories across distributed microservices. To mitigate this risk, you should implement centralized schema registries that function as a single source of truth for all components in the pipeline. When a schema evolves, the registry ensures that downstream data consumers are aware of the structural changes, preventing the corruption of the lineage chain. If your analytical platform expects a specific format to maintain privacy features like masking or encryption, any breaking change in the upstream producers will immediately invalidate your compliance posture. By automating the validation of these schema versions against your inventory, you ensure that personal data remains labeled correctly regardless of how many times it is aggregated or moved between clouds. Debugging a broken chain requires scanning these metadata headers to identify the exact hop where the association between the data and its consent policy was lost. Beyond infrastructure, we must address the logical connection between the data and the user's intent. When a user provides consent for a specific data processing activity, that consent is effectively a piece of state attached to the data at the point of origin. Your lineage mechanism must ensure that this state is propagated alongside the data as it moves through various staging environments and analytical engines. If an ETL pipeline moves a record from an operational database to a data warehouse, the system must recognize that the consent flag is a dependency for the data to be legally usable in that destination. If we cannot prove that the data being analyzed has the matching active consent status, we have effectively failed our privacy engineering obligation. This requires integrating your consent management platform directly into your data orchestration workflows so that lineage is automatically updated whenever consent is withdrawn or modified by the user. Maintaining this level of detail requires a combination of automated instrumentation and clear architectural design. You may use open-source tools that track object movement or proprietary solutions that hook into your cloud provider's logging infrastructure, but the outcome should always be a graph-based representation of your data flow. If you can visualize every input, every transformation function, and every destination, you can accurately answer questions about provenance and purpose. This is particularly relevant when performing data impact assessments, as the lineage graph reveals exactly which downstream systems are impacted if a specific data source is flagged for deletion. If your technical team treats lineage as an afterthought, you will eventually find yourselves unable to demonstrate accountability, regardless of how strong your existing security controls or encryption measures might seem. Build your pipelines with observability at the center, and the compliance requirements will naturally be easier to fulfill. See you in the next session. Welcome to the chapter on risk quantification, where we transition from subjective assessments to empirically rigorous methods for measuring technological privacy exposure. We will focus on translating privacy vulnerabilities into measurable business metrics using structured statistical models. In an engineering context, qualitative labels like high, medium, or low risk are rarely sufficient for making informed infrastructure decisions. When you need to justify the cost of implementing a privacy-preserving architecture, you are effectively speaking the language of engineering trade-offs, which demands precision. We move beyond narrative risk descriptions by adopting factor analysis of information risk, often referred to as FAIR, to model privacy-specific threats. This approach requires us to decompose risk into two primary components: loss, event frequency, and magnitude of loss, by identifying the probability of a privacy breach occurring and the potential impact if that event manifests. We establish a baseline for our system's exposure. Mathematical rigor ensures that our privacy strategy aligns with the broader financial and operational governance targets of the enterprise. To implement this concretely, you must start by defining your loss event scenarios based on specific system vulnerabilities. For instance, if your application stores PII in an unencrypted repository, the threat isn't just a vague notion of data loss. It is a specific frequency of unauthorized access attempts against a known system vulnerability. You quantify threat capability, the skill and intent of the actor, against the system vulnerabilities that allow a threat to exploit a control. We calculate threat capability by evaluating historical incident data, or, in the absence of internal telemetry, industry-standard threat intelligence feeds. The vulnerability of the system is then modeled as the probability that a threat attempt results in a loss event. When you multiply these variables, you move from mere speculation toward a legitimate statistical probability of impact. The next phase involves translating these statistical probabilities into financial metrics that stakeholders can appreciate. We estimate magnitude by calculating both the primary loss, such as regulatory fines or remediation costs, and secondary losses, like reputational damage or churn. If an incident affects a record set of 100,000 users, you multiply the per-record cost by the probability of exposure to derive an expected loss value. This allows you to present findings as a definitive financial risk metric, such as an annualized loss expectancy. By aligning these calculations with the risk appetite defined by company leadership, you provide a clear justification for prioritizing specific privacy-enhancing technology deployments. This rigor removes the ambiguity that often stalls privacy initiatives in the development cycle. Finally, you should move toward automating these insights using real-time risk dashboards that aggregate systemic signals. A static spreadsheet is insufficient for modern agile environments where infrastructure changes daily. Integrate your risk measurement tools with your CI/CD pipelines to monitor for drift against your predefined risk thresholds. When a code deployment introduces a new data flow that exceeds an established loss expectancy limit, the system should trigger an immediate alert for engineering intervention. This approach treats privacy risk as a telemetry stream, essentially making it a first-class citizen of your observability stack. By viewing risk through this mathematical lens, you ensure that privacy is not just a policy requirement, but a measurable component of your operational excellence. I look forward to seeing you in the next session. Welcome back. In this session, we will examine the technical implementation of data minimization to reduce organizational risk and technical debt. Data minimization is often misunderstood as a simple policy mandate, but from an engineering perspective, it is a structural constraint that must be enforced at the earliest possible point of data ingestion. When we design systems, we often fall into the trap of collecting everything just in case we need it later, which creates a massive attack surface and increases the burden of compliance. Instead, we should view every data point as a liability that requires specific justification to process and maintain. By implementing aggressive input sanitization, we effectively act as a filter that rejects extraneous information before it ever touches our persistent storage layers. This requires developers to define strict schemas where only the fields absolutely necessary for functionality are accepted and everything else is silently dropped or logged as an error. If an API contract specifies only a user identifier and a timestamp, our code should ignore any additional metadata, such as device identifiers or granular location variables at the gateway level. Automated data reduction protocols should be integrated directly into your ingestion pipelines to ensure that technical enforcement is consistent and repeatable. One practical pattern involves establishing real-time filtering rules on your API gateways to scrub telemetry data before it reaches your backend services. By stripping out unnecessary variables at the periphery, you prevent sensitive data from ever becoming part of your database commit cycle. This approach is superior to periodic batch cleanup jobs because it ensures that the data hoarding behavior is physically impossible within the operational context of the application. You might consider configuring your ingestion middleware to inspect incoming JSON payloads and strip out fields that do not conform to your predefined minimization policy. This deterministic approach provides a clean separation between the data required for business logic and the noise that often accumulates in log structures and database tables over time. Once data has been ingested, the focus must shift to maintaining that minimization through dynamic lifecycle management, specifically via time-to-live policies. Data that is no longer relevant to the primary processing purpose should not linger in caching structures or operational data stores, as its existence represents a persistent risk to the privacy of the data subject. You can implement automated expiration policies by setting headers in your caching layers, or by utilizing native database features that support row-level TTL attributes. When a record passes its usefulness threshold, the system should automatically transition that data to an immutable deletion state, rather than relying on manual intervention. This logic should extend from your active production environment into your backup archives, where the cost and risk of storage grow exponentially. By aligning your retention schedules with the actual technical utility of the data, you reduce your organization-wide footprint and make incidents significantly less damaging. Programming for privacy also means questioning the default behavior of our data models and field definitions. We often allocate fields for potential future use, such as providing a large character limit for a description field that is rarely utilized to its full extent. By enforcing truncated data entry fields at the UI and business logic tiers, we limit the capacity for users to inadvertently store unstructured personal information where it doesn't belong. This is a form of input validation that serves the dual purpose of application security and data minimization. I recommend reviewing your persistent entities to identify where you are storing data that is seldom accessed but frequently replicated. If you find that a significant percentage of your database is composed of null values or stale information, your system architecture is likely violating the core principles of minimization. Implementing these controls requires a shift in the developer mindset, moving away from a repository-first approach toward a privacy-by-design methodology. When you are configuring your database schemas or API endpoints, ask yourself what the absolute minimum set of attributes is required for a transaction to succeed. If a specific device identifier is only used for session-based fraud detection, it should exist only in memory or a volatile short-term cache rather than being persisted in a relational store. By strictly enforcing these collection boundaries, you prevent the accumulation of sensitive data that, if breached, could lead to significant regulatory exposure. The programmatic enforcement of these rules might involve writing interceptors or middleware that validates the integrity of the data stream before it passes into your repository layer. This level of technical rigor ensures that your application remains compliant by default, regardless of individual user actions or secondary system processes that might otherwise aggregate more data than intended. See you in the next lecture. Hello again. Let us explore the domain of obfuscation tactics and how we can effectively shield sensitive data within high-throughput production environments. We will discuss specific engineering approaches to ensure that sensitive fields remain protected without compromising the functional requirements of your underlying systems. When we approach the challenge of protecting personally identifiable information in a live database, we must distinguish between permanent transformations and dynamic, context-aware masking. Format-preserving encryption stands out as a particularly elegant solution because it maintains the length and character set of the original data, which allows legacy applications to process encrypted values without needing a complete refactoring of the schema. In contrast to standard encryption, which often produces long binary strings that break validation logic, format-preserving encryption keeps a credit card number looking like a credit card number. This is crucial when you have hundreds of downstream services relying on fixed-width schemas or specific input constraints. By using a properly configured block cipher that operates on the same domain as the plaintext, Engineers can ensure that the ciphertext remains valid in terms of format, thus avoiding application-level errors. This ensures that the privacy layer remains transparent to the business logic, effectively decoupling sensitive data handling from operational processing. Moving beyond encryption, we often turn to tokenization, which is arguably the most robust method for decoupling PII from the business process. In a vaulted tokenization architecture, a secure database, or vault, maps sensitive data to a non-sensitive token, acting as the single source of truth for re-identification. While this provides a high degree of control, it creates a significant architectural bottleneck as every tokenization request must traverse the network to hit the vault. To address these performance concerns, vaultless tokenization engines utilize algorithms that calculate tokens deterministically without storage, relying on cryptographically secure functions to map sensitive values. When we design these systems, we must ensure that the token translation server operates within a strictly defined network boundary. This server assumes the role of an authorization gate, determining who or what service is permitted to perform the detokenization process. By ensuring that peripheral systems interact primarily with these safe, non-sensitive tokens, we fundamentally reduce the scope of data residency requirements for those systems. For environments that require real-time visibility without permanent data modification, we rely on database view masking layers and proxy-based solutions. A proxy-based masking agent acts as an intermediary layer between the database client and the data store, inspecting every incoming query. Based on the authenticated database user's context, the proxy dynamically modifies the result set to redact, hash, or mask specific sensitive fields. For example, a system administrator might only see the last 4 digits of a social security number, while a specialized compliance officer would have the necessary credentials to view the full, unmasked record. This implementation avoids the pitfalls of static data masking, where you physically overwrite data in the production table, an approach that is rarely appropriate for true production environments. Instead, we treat the production data as inviolate while using the proxy or view layer as a dynamic filter. This strategy ensures that we respect the principle of least privilege, providing access to raw data only when it is strictly required by the specific user's job function. Designing these architectures requires a disciplined approach to managing the lifecycle of sensitive data as it flows through the various tiers of our infrastructure. When we design these data paths, we must assume that the network is inherently hostile and perform our tokenization as close to the point of entry as possible. By replacing sensitive PII with tokens early in the lifecycle, we ensure that the vast majority of our internal microservices and analytical tools never touch the clear text version of the data. This approach requires careful coordination between the security team and the developers who own the peripheral systems to ensure that they can perform their tasks using only the tokenized values. Furthermore, we must monitor the performance impact of these transformations, as introducing multiple cryptographic lookups or proxy rewrites can introduce significant latency into high-throughput database operations. Our goal is to balance the absolute security of the sensitive data with the non-negotiable availability and throughput requirements of the production system. I look forward to discussing how these tactics align with anonymization models in our upcoming segment. Welcome back. Today we are diving into the mathematical rigors of anonymization models to protect structured datasets. We will analyze the core mechanisms of K-anonymity, L-diversity, and T-closeness to better understand their practical limitations in real-world engineering. To understand the concept of K-anonymity, we must first define quasi-identifiers, which are bits of information that, when combined, can uniquely identify an individual. Think of a medical dataset containing ages, zip codes, and genders. An attacker often possesses auxiliary information, like a voter registration list, which serves as the side channel for a linkage attack. A release is considered to have K-anonymity if the information for each person contained in the release cannot be distinguished from at least K-1 individuals whose information also appears in the release. To achieve this, we typically employ suppression, which removes data, or generalization, which replaces specific values with broader categories. For instance, replacing specific ages like 28 and 29 with an age range of 20 to 30 effectively masks the individual data point. However, this mathematical guarantee protects against identity disclosure, but fails to address attribute disclosure, which is a critical distinction for a privacy engineer. If all members of a k-anonymized group share the same sensitive attribute, such as having a specific chronic disease, the privacy is compromised despite the k-anonymity threshold. Because k-anonymity is vulnerable when sensitive attributes lack sufficient heterogeneity, we turn to L-diversity as a necessary, albeit complex, extension. An equivalence class satisfies L-diversity if it contains at least L well-represented values for the sensitive attribute, meaning that an attacker cannot easily infer the sensitive value by simply knowing the group membership. Imagine a group of 10 people, all aged between 40 and 50, living in the same zip code who all suffer from the same rare neurological condition. While this set might satisfy k-anonymity with k equal 10, it fails the L-diversity check spectacularly because there is no variation in the sensitive attribute. We improve this by ensuring that the distribution of sensitive values is diverse enough to provide uncertainty for any observer. Yet, L-diversity itself is susceptible to skewness attacks and similarity attacks, where the distribution of sensitive values is biased toward a specific outcome or where values are semantically similar. Even if the sensitive values are diverse, if they all reside at the same end of a spectrum, the privacy protection remains fundamentally fragile. The T-closeness model attempts to reconcile the shortcomings of the previous two models by requiring the distribution of a sensitive attribute in any equivalence class to be close to the distribution of that attribute in the overall dataset. Formally, an equivalence class is said to have T-closeness if the distance between the distribution of a sensitive attribute in the class and the distribution of the attribute in the whole table is no more than a threshold T. This approach prevents attackers from using background knowledge about the public distribution of traits to isolate individuals within a subset. By enforcing a global distribution, we ensure that an observer gains no additional information from knowing which equivalence class a record belongs to, aside from what they could have deduced from the entire population. This is highly effective against skewness attacks, though it comes at the cost of significantly higher data utility loss compared to simpler models. Balancing the granularity of our data against the mathematical strength of the anonymization requires a constant calibration of our threshold variables based on the specific risk profile of the data. While these models provide a structural framework for privacy, we must remain vigilant about the algorithmic trade-offs they demand. Every time we generalize a variable or suppress a data point to meet our K, L, or T requirements, we are intentionally degrading the statistical fidelity of the dataset for the sake of privacy. A successful implementation necessitates a deep understanding of the intended use case, because a dataset rendered perfectly anonymous for one function may be useless for another dependent application. We must also acknowledge that no model provides a static shield against all future re-identification techniques, especially as computational power increases and new datasets become available for linkage. The primary goal is to shift the risk from certainty of identification to an acceptable level of ambiguity that renders large-scale re-identification economically or logically prohibitive for a potential adversary. As engineers, our work is not to create a perfectly uncrackable data cache, but to design a controlled environment where the privacy risk is inherently bound by these calculated mathematical constraints. See you in the next lesson. Welcome back. In this chapter, we explore the formal mathematical guarantees of differential privacy and how they allow us to extract insights from datasets without compromising individual records. Differential privacy provides a rigorous mathematical framework for quantifying the privacy loss associated with releasing aggregate information from a dataset. Unlike traditional de-identification methods, which often struggle against auxiliary information attacks and linkage, differential privacy is fundamentally concerned with the influence that a single individual's data has on the output of a query. We define a mechanism as differentially private if the inclusion or exclusion of any one person in the underlying database does not significantly alter the probability distribution of the output. This is typically governed by the privacy budget, denoted by epsilon, which sets a hard upper bound on the amount of information that can be leaked. A smaller epsilon value provides stronger privacy guarantees but inevitably leads to lower utility in your statistical results. If you imagine a query asking for the average salary of a specific department, differential privacy ensures the result remains stable even if we remove or add one person. thereby preventing an observer from confirming an individual's presence in that dataset. To achieve these properties, we must inject calibrated statistical noise into our query results or the underlying data itself. There are two primary mechanisms for this: the Laplace mechanism and the Gaussian mechanism. The Laplace mechanism is best suited for scenarios where we want to satisfy pure epsilon differential privacy, meaning that we do not allow any probabilistic failure in our privacy guarantee. For a specific query, we calculate the sensitivity, defined as the maximum change one record can induce on the query result, and we draw noise from a Laplace distribution scaled by this sensitivity divided by epsilon. The Gaussian mechanism, on the other hand, is often used in situations where we can tolerate a small probability of privacy failure known as delta. This relaxed requirement allows for more complex, high-dimensional queries, as the Gaussian distribution often provides tighter error bounds in large-scale machine learning or iterative analytical tasks. Choosing the correct distribution depends entirely on your specific risk appetite and the architectural requirements of your pipeline. When we scale these mechanisms to modern big data pipelines, we must distinguish between local and central differential privacy. In central differential privacy, a trusted aggregator collects raw data from clients and applies the noise before releasing any statistics. This approach generally yields higher data utility because the noise is applied to the final result rather than to the individual records before they are even stored. Local differential privacy shifts the burden to the client device, where noise is added to the data before it ever reaches your server. While this ensures that no raw data is ever exposed to the central system, it requires a significant amount of noise to reach statistical significance, which can degrade the accuracy of aggregate insights. Architects must decide if their infrastructure supports the existence of a trusted central server or if the environment mandates that the system remains agnostic of raw data types at the point of ingestion. Managing the privacy budget over time is arguably the most complex aspect of implementing these systems. If you perform multiple queries on a single dataset, the privacy loss is additive, meaning that every operation consumes a portion of your budget until you hit your defined epsilon limit. Continuous data analysis pipelines require automated budget enforcement mechanisms that track the total sensitivity of all operations executed against the protected data. Failing to account for this composition results in a privacy leak where subsequent queries, when combined, allow for the reconstruction of individual identities through triangulation. You should implement a centralized monitoring service that computes the cumulative sensitivity of all queries made by analysts to ensure the total privacy loss remains within your established policy. This requires integrating privacy accounting directly into your database query interface, ensuring that no query is executed if it exceeds the remaining privacy budget for that period. As you refine your implementation, remember that mathematically sound privacy is only as effective as the engineering that surrounds it. You need to verify that your sensitivity calculations correctly account for the potential range of all possible query inputs. If your implementation underestimates the sensitivity of a function, the noise injected will be insufficient to mask the influence of specific values, rendering your privacy budget management ineffective. Additionally, you must be cautious about the metadata surrounding your queries, as even the frequency or timing of reports can inadvertently leak information about the underlying data trends. Effective differential privacy requires an end-to-end approach where the mathematical proofs are mirrored by strict access controls and robust logging at the database architectural level. By treating privacy as a variable of your analytical output, you transform security from a perimeter concern into a property of the data itself. See you in the next section. Welcome back. Today we examine the technical nuances of pseudonymization and how to implement it within a secure architecture. Pseudonymization is a data processing technique that replaces a natural person's identifying information with a surrogate value, known as a pseudonym, so that the data cannot be attributed to a specific person without the use of additional information. Unlike permanent anonymization, which removes the possibility of identifying an individual entirely, pseudonymization remains reversible if the holder of the key or lookup table is compromised. From a regulatory perspective, such as under the GDPR, Pseudonymized data is still considered personal data because the original subject remains identifiable through technical means. Therefore, your engineering objective is to ensure that these secondary identifiers are stored separately and protected by distinct technical and organizational measures. By maintaining this separation, you satisfy the regulatory requirement that additional information enabling re-identification must be kept separately from the technical datasets. This decoupling is the fundamental requirement for ensuring that your pseudonymization strategy actually functions as a privacy-enhancing control rather than merely security by obscurity. When we construct the architecture for this, we must rely on robust cryptographic practices rather than simple database mapping. The most effective approach involves using hash-based message authentication codes, or HMAC, to derive pseudonyms from primary identifiers like email addresses or government IDs. By utilizing a secret key combined with a cryptographic hash function, you ensure that the same input consistently produces the same pseudonym while remaining computationally infeasible for unauthorized parties to reverse engineer the original ID. However, static keys present a systemic risk because a compromise of the key exposes the entire identity mapping for the whole dataset. Consequently, you must implement dynamic salting management, where different salts or keys are used for different datasets or processing windows. This approach limits the blast radius of a potential compromise and forces an attacker to perform a much more complex targeted de-identification rather than a global mapping breach. The actual infrastructure supporting these pseudonyms needs to be modular to prevent what we call data spills in the analytical layers. Your primary application databases should feed identity data into a dedicated, hardened translation service that manages the HMAC operations and maintains the secure vault of keys. Downstream analytical tools or data warehouses should only ever receive the tokenized pseudonyms, never the raw identifiers or the keys themselves. This is achieved by creating an isolated indexing architecture where the translation logic resides within a private, highly restricted execution environment. Access permissions for this translation service must be strictly audited and limited to the absolute minimum number of service accounts necessary for operational continuity. If an analyst wants to understand behavioral trends, they perform their queries on the pseudonymized dataset, effectively decoupling the behavioral profile from the actual human identity held in your secure vault. Auditing the translation request pipeline is the final piece of the architectural puzzle that many engineers overlook during the initial design phase. You need to log every request to the translation service, particularly those involving re-identification lookups, to maintain accountability and detect potential anomalous behavior. These logs must be write-only for the service and stored in a location where the keys themselves are not accessible to those with administrative rights to the data. By treating these translation services as a black box with strictly monitored inputs and outputs, you create a controlled interface for data interaction. It is not enough to hide identifiers. You must be able to prove through your audit logs that the data subjects were not exposed during processing. This methodical approach to pseudonymization provides the technical evidence required for regulatory compliance while maintaining the utility of your datasets for big data analytics. See you in the next lecture. Hello. Let's explore the critical technical discipline of validating our anonymization efforts through the lens of re-identification defense. This chapter focuses on how we stress test our data protections by simulating the exact tactics a motivated adversary would employ against our pseudonymized datasets. In an ideal world, anonymization would be a static state where data is rendered permanently unidentifiable. In practice, however, data is a living artifact that exists within a broader ecosystem of interconnected information. Re-identification defense is the technical process of treating anonymization as a continuous verification problem rather than a one-time configuration task. We must assume that an adversary has access to various auxiliary datasets and possesses the computational power to perform linkage attacks. A linkage attack occurs when an attacker combines supposedly anonymous data with identifiable auxiliary data to reconstruct the identity of the original data subjects. If we do not actively test for these vulnerabilities, we cannot honestly claim our datasets are resilient against modern threats. The core of a re-identification defense strategy is the execution of simulated linkage attacks. We start by mapping our internal masked records against known external data vectors, such as public voter registration logs, social media metadata, or commercial marketing sets. Even when we sanitize specific identifiers like names or social security numbers, quasi-identifiers like birth dates, zip codes, or gender remain susceptible to triangulation. An attacker does not necessarily need a perfect match to break our privacy controls. They often utilize probabilistic matching algorithms to assign likelihood scores to record pairs, eventually narrowing down individuals until they obtain a high confidence match. Our role as privacy engineers is to anticipate these correlations before an attacker discovers them in the wild. To support this effort, we employ automated machine learning scripts that scan our datasets for latent patterns. These scripts effectively reverse engineer our generalization rules by identifying where our data suppression is insufficient or where binning techniques have created outliers. For instance, if you generalize ages into 5-year buckets, an attacker might still isolate a specific individual if they happen to be the only person in a particular zip code belonging to that narrow age range. The automated scripts calculate the uniqueness of records across these multidimensional spaces to determine how easily a single record can be isolated. By establishing a baseline for this uniqueness, we gain a technical metric that quantifies the actual risk profile of our database. Evaluating the utility of data versus the risk of re-identification creates an inevitable tension. As we increase the strictness of our obfuscation, we inevitably strip away the nuance that makes the data useful for analytics or machine learning models. Therefore, we utilize data utility metrics alongside our vulnerability scores to ensure we aren't destroying the business value of the data in our pursuit of privacy. This necessitates a continuous scoring framework that tracks the evolution of data sensitivity as new datasets are integrated into the pipeline. If we introduce a new batch of data or change the formatting, the scoring framework must automatically flag the change. This feedback loop is essential for maintaining the posture of a system that is constantly changing. Engineers should establish automated alerts that trigger whenever the systemic re-identification risk exceeds the organization's predefined threshold. This is not simply a matter of checking for the presence of PII, but rather calculating the entropy of the dataset to see if the overall dispersion of values has become too indicative of specific individuals. When an alert fires, it signals that the generalization or pseudonymization approach is no longer sufficient and that further masking or k-anonymity adjustments are necessary. Effectively, we are creating a form of red teaming for our data architecture that runs in the background of our standard development lifecycle. This technical vigilance is the only way to evolve our privacy posture alongside the increasing availability of public data. See you in our next technical discussion. Welcome back. Today we will examine the technical mechanisms of access management and how they enforce privacy. Access management is the gatekeeper of the digital enterprise, and its efficacy directly determines whether privacy policies remain mere suggestions or become enforced reality. When we speak about identity and access management in a privacy-centric context, we are shifting our focus from simple authentication to the granular orchestration of visibility. A robust system ensures that every request is validated against the principle of least privilege, preventing unauthorized exposure of sensitive user data. Traditional models relied on static permissions, but modern privacy engineering requires dynamic systems that understand context. By designing systems that evaluate attributes in real time, we can restrict access to data based on current necessity rather than historical status or tenure. This is not just about keeping intruders out, but about ensuring that internal personnel only touch what is essential for their immediate operations. Achieving this requires moving away from broad, monolithic roles and embracing architectures that support granular scoping and temporal constraints. Role-based access control has been a historical staple in enterprise security, yet it often falls short of the privacy requirements mandated by modern regulations. The primary issue with traditional roles is role explosion, where the number of unique combinations grows beyond maintenance capacity. When a role is assigned, it often grants excessive permissions that a user only needs for a fraction of their daily activities. To mitigate this, we should look toward attribute-based access control as the superior alternative for privacy-sensitive environments. ABAC functions by evaluating a combination of subject attributes, resource attributes, and environmental conditions before granting access. For example, an administrator might have the role of a support agent, but their access to sensitive records is only enabled if the request originates from a trusted network during standard working hours. This logic allows us to collapse hundreds of static roles into a few flexible policies that adapt to the reality of the user's current situation. Zero Trust architecture fundamentally changes the underlying assumptions of our internal network borders. In this model, you assume that the internal network is just as hostile as the public internet, requiring every request to be authenticated and encrypted regardless of its source. This philosophy mandates that we implement microsegmentation, ensuring that even if a single service is compromised, the attacker cannot pivot to sensitive data stores. Beyond basic authentication, we must integrate just-in-time privilege elevation, which ensures that administrative rights are only granted for the duration of a specific task. Once the task is complete, the access is automatically revoked, minimizing the window of opportunity for credential misuse. This approach is highly effective for reducing the risk of internal threats and accidental data leakage during administrative maintenance. Building such an environment requires moving toward federated identity protocols that rely on standard-based assertions rather than legacy proprietary credentials. Federated identity protocols such as SAML 2.0, OAuth 2.0, and OpenID Connect provide the infrastructure needed to maintain a centralized authority while granting fine-grained authorization scopes. By using OpenID Connect for identity and OAuth 2.0 for authorization, developers can issue scoped access tokens that limit the amount of data shared with downstream services. An authorization scope acts as a contract, explicitly defining what the client application is allowed to read or modify, such as preventing an application from seeing a user's full date of birth when it only needs a verification of their age. Furthermore, we must implement automated credential lifecycle management to ensure that rotating secrets do not become an operational bottleneck. When we synchronize centralized directories, we must ensure these engines are configured with strict data minimization filters so that only necessary identity information is replicated across the ecosystem. Every move toward automating these processes reduces the risk of human error, which remains a primary contributor to large-scale privacy incidents. When engineers design access policies, the objective should always be to reduce administrative data visibility to the absolute minimum required for operational fulfillment. This means audit logs, monitoring tools, and management dashboards must be configured to mask or truncate sensitive fields by default. We should treat access to the system metadata with the same level of scrutiny as access to the production data itself. If a system administrator does not need to see the clear text PII of a user to troubleshoot a network connectivity issue, the dashboard must suppress that data entirely. Applying these constraints requires tight integration between our policy engines and our application code, ensuring that the authorization logic is decoupled from the business logic. Maintaining this posture allows organizations to demonstrate compliance during audits and provide objective evidence that they have taken every technical precaution to isolate user privacy. Through these combined disciplines, we build an infrastructure that is both resilient to external attacks and respectful of individual privacy rights. See you in the next lecture. Welcome back. We are moving into the technical implementation of cryptographic controls to safeguard personal data throughout its entire lifecycle. When we talk about protecting personal information, we must consider the state of the data, specifically whether it resides at rest or is actively moving across network segments. At rest, such as in a database or an object storage volume, your primary defense is robust encryption, typically employing the advanced encryption standard with a 256-bit key length. AES 256 remains the industry standard because of its computational efficiency and resistance to brute force attacks, provided the implementation is correct. However, simply encrypting a disk is rarely sufficient for high-assurance privacy engineering. You should aim for field-level encryption for sensitive attributes like names, emails, or financial records. This strategy ensures that even if an attacker gains unauthorized access to the database layer or a backup file, the data remains ciphertext, rendering it useless without the corresponding keys. By decoupling decryption rights from database administration, you enforce a form of principle of least privilege that significantly narrows your attack surface. Remember that cryptographic implementations are prone to failure if hard-coded secrets are present in your codebase. Instead, always leverage secure environment variables or a dedicated secret management service to inject keys at runtime, effectively keeping sensitive material out of your version control systems. Transitioning to data in transit, the current gold standard for securing network communications is Transport Layer Security 1.3. Unlike its predecessors, TLS 1.3 strictly prohibits the use of insecure, legacy features that have historically made protocols vulnerable to downgrade attacks or interception. When you configure your web servers or internal microservices, you must explicitly specify strong cipher suites that utilize authenticated encryption with associated data, or AEAD. Modes like Galois/counter mode, commonly referred to as GCM, provide both confidentiality and integrity, ensuring that the payload has not been tampered with while it was being transmitted. You should systematically disable older protocols such as SSL 3.0, TLS 1.0, and TLS 1.1, as these are no longer considered cryptographically sound for protecting personal information. This configuration requires a disciplined approach to server hardening, where you test your connections against modern security standards to ensure compatibility without sacrificing safety. While it might seem easier to allow broad legacy support, doing so leaves a door open for attackers to force a weaker connection and decrypt your traffic in real time. In advanced privacy engineering, we are frequently asked how to extract value from personal data without exposing the raw information to the processing system. This is where cutting-edge approaches like homomorphic encryption and secure multi-party computation become relevant. Homomorphic encryption allows an analyst to perform mathematical operations on encrypted data, such as summing values or calculating averages, while the underlying data remains in its encrypted state. When these operations are complete, the resulting output can be decrypted by an authorized party, revealing the answer without the processing environment ever having perceived the plain text. Similarly, secure multi-party computation involves multiple parties collaboratively computing a function over their inputs while keeping those inputs private from one another. These technologies represent a departure from traditional decrypt then process workflows and are essential for privacy-preserving analytics in modern architectures. While computationally expensive and more complex to integrate than standard AES configurations, they provide a powerful mechanism to satisfy the conflicting demands of data utility and strict privacy compliance. Building these architectures requires a mindset that views cryptography not just as a checkbox requirement, but as a dynamic component of your application ecosystem. You must treat your cipher choice and your key management strategy as an integrated part of your broader threat model. It is not enough to select the right algorithm. You must ensure the entire pipeline, from the moment data is captured to the point where it is finally deleted, maintains this high level of integrity. By choosing modern primitives like GCM for authenticated encryption and mandating TLS 1.3, you move beyond mere compliance toward a demonstrably secure infrastructure. As we look at these layers of protection, consider how every decision at the code level impacts the privacy of the end user. This technical depth is what separates a mature privacy program from one that relies on theoretical protections. I will see you in the next lecture. Welcome back to our exploration of privacy engineering, specifically focusing on the technical controls that secure our data. In this segment, we will delve into the critical domain of key management systems and how they serve as the backbone for cryptographic integrity within modern architectures. When we talk about the life cycle of cryptographic keys, the first step is secure key generation, which must rely on cryptographically strong random number generators rather than standard software pseudorandom functions. A robust key management system treats the generation process as an immutable event, ensuring that the entropy source is sufficiently high to withstand brute force attempts. Once generated, these keys need to exist within secure storage boundaries, ideally isolated from the application tier that processes the actual data. Hardware security modules, or HSMs, provide this physical or logical separation by ensuring that the private or master keys never leave the hardened environment in plain text. By offloading cryptographic operations to an HSM, we ensure that even if an application server is fully compromised, the underlying material used for decryption remains encrypted and protected from extraction attempts. Managing keys at scale requires moving away from manual interventions toward automated rollover policies that trigger based on time-based intervals or specific volume thresholds of processed data. Envelope encryption is the standard pattern for this, where a data encryption key is used to encrypt local records, while that key itself is encrypted by a key encryption key managed by your central service. This hierarchy allows for massive scalability because you only need to protect the master keys within your hardware security module, while the data encryption keys are stored alongside the data they protect. When a rollover is initiated, the system decrypts the data encryption key using the current master key and then rewraps it with a new master key version. This automated transition ensures that data remains accessible even as the underlying cryptographic material evolves over its operational lifespan. Access control within your key management strategy must strictly enforce the principle of least privilege, specifically by ensuring a separation of duties between key users and key administrators. Application developers and standard system administrators should never have the capability to export, view, or rotate master keys manually. Their access should be restricted to calling specific encryption or decryption APIs. This is often achieved through identity-based access control, where the KMS validates the identity of the service account or machine identity before completing an operation. By defining strict boundaries, you prevent lateral movement where an attacker who gains elevated access to a database cluster is unable to pull the master keys required to unlock the archived volumes. Every request directed toward the key management interface must trigger an immutable log entry that records the identity of the requester, the operation performed, and the timestamp, providing an audit trail that is critical for security monitoring. In the context of cloud-native environments, the integration pattern involves interacting with regional or global KMS APIs that manage the underlying storage and HSM lifecycle for you. These providers offer interfaces to perform cryptographic transformations without requiring your code to handle raw key bytes in memory, significantly reducing the surface area for leaks or memory dumping attacks. When you architect for large database volumes, your focus should be on the policy governing the envelope, ensuring that the overhead of key rotation does not introduce unacceptable latency to your primary ingestion pipelines. You must document the key policies, including the expiration criteria and the revocation procedures, as part of your system lifecycle documentation. Maintaining this technical rigor is the only way to ensure that your privacy controls are not just theoretical, but functionally resilient against the threats identified during your earlier risk assessments. I will see you in the next lecture. Welcome to this chapter, where we will examine the technical requirements for designing and maintaining robust audit logging architectures for privacy compliance. We're going to explore how to track data access while ensuring the integrity of the collected telemetry. In this session, we examine the construction of centralized, tamper-proof audit logging architectures designed to monitor data access consistently across your entire infrastructure. An audit log is not merely a collection of text files. It is a critical instrument for accountability and compliance, requiring an architecture that persists through system failures and malicious interference. You should prioritize asynchronous logging pipelines to separate the concerns of application execution from diagnostic reporting, thereby preventing logging overhead from impacting production performance. By offloading log serialization to a sidecar process or an external message broker, you ensure that the application remains responsive even under high load. This decoupling is essential when dealing with granular event data, such as resource access requests or privilege escalations, which must be captured without introducing latency into your hot path. When logs are processed asynchronously, the trade-off is the potential for minor delivery delays, but this is a manageable cost compared to the risks incurred by synchronous I/O blocking. Securing the integrity of these log stores is the next logical step in our architectural design. Once data is captured, it is susceptible to tampering, which compromises its utility for forensic analysis and privacy auditing. To mitigate this risk, you should design storage layers that utilize write-once-read-many (WORM) configurations, which physically or logically prevent the modification or deletion of records once they are committed. Beyond storage-level protections, you must incorporate cryptographic verification methods, such as chaining log entries through block hashing. By calculating a hash for each log entry that includes the hash value of the preceding entry, you create an immutable evidentiary chain that alerts you immediately if any historical record has been altered. This cryptographically anchored ledger provides high assurance that the audit trail remains pristine, even if an attacker gains administrative access to the underlying storage server. You are effectively building an append-only system where the history of data access becomes verifiable and resistant to deletion. A significant challenge in privacy engineering is ensuring that audit logs do not inadvertently become a repository for sensitive information. Capturing a raw HTTP request header or a database query parameter can easily result in the logging of PII, which creates a privacy compliance paradox. You must implement automated masking filters at the ingestion layer ahead of the storage backend to identify and sanitize patterns that resemble sensitive data. These filters should employ regex-based patterns or more sophisticated tokenization services to redact identifiers like social security numbers, email addresses, or account IDs before they are persisted. A proactive approach involves defining a strict schema for log telemetry, where only allowed, non-sensitive fields are indexed and the rest is discarded by the parser. This design choice shifts the burden from manual auditing of logs to a systematic exclusion policy, ensuring that your security audit trail respects the principle of data minimization while remaining useful for investigators. Once your structured telemetry is secured and sanitized, the final step involves streaming this data into a centralized security information and event management platform for analysis. Raw logs have limited value unless you have the tooling to aggregate them and correlate events across disparate systems. Through SIM integration, you can define specific queries to monitor for anomalous data scraping behavior, such as a single user identity accessing an abnormal volume of records in a short time frame. This capability is vital for detecting compromised accounts or unauthorized automated processes that attempt to bypass application layer controls. By treating your logs as streams of structured data, such as JSON objects with consistent schemas, you enable complex correlation rules that provide deep visibility into the usage patterns of your environment. This holistic view transforms your audit logging from a passive compliance requirement into an active threat detection mechanism within your privacy infrastructure. See you in the next lecture. Welcome to our exploration of network security, where we examine how to architect robust defenses for data-sensitive environments. We will focus on how to technically isolate traffic and secure infrastructure through advanced networking principles. In the modern landscape of software development, perimeter security is no longer merely about a hardware firewall sitting at the edge of your corporate office. Effective network security for privacy engineers requires a shift toward microsegmentation, where we treat the internal network as a series of untrusted zones. By programmatic deployment of these segments, we ensure that even if one component of an application is compromised, the breach remains contained within a restricted virtual local area network. This strategy relies heavily on the use of virtual private clouds to enforce strict boundary isolation between public-facing web tiers and your back-end processing zones. You should approach your infrastructure as code, using automation scripts to manage these boundaries rather than manual configuration, which drastically reduces the risk of human error. Next-generation web application firewalls serve as our first line of defense against application layer attacks that traditional firewalls often overlook. Unlike legacy systems that rely primarily on basic signature matching, these modern tools utilize deep packet inspection to analyze the traffic payload in real time. When you configure a secure reverse proxy, you are essentially establishing a controlled gateway that intercepts traffic before it reaches your sensitive data stores. This allows you to sanitize requests, mask backend server identities, and block malicious injection attempts before they ever encounter your application logic. Furthermore, implementing automated DDoS mitigation patterns ensures that your services remain available for legitimate users even during periods of heavy volumetric stress. Visibility remains an equally critical component of a mature security posture, as you cannot protect what you cannot observe or identify within your network topology. Continuous vulnerability scanning routines are essential to automatically discover open ports that might have been inadvertently exposed by a developer during an ad hoc deployment. By integrating these scanning tools into your infrastructure pipelines, you can ensure that unpatched network services are flagged and remediated before they become entry points for unauthorized actors. This proactive approach to network monitoring turns your security posture from a stagnant, reactive state into a dynamic, ongoing process of verification. Your goal is to establish a system that continuously validates the state of its own network boundaries against the desired secure configuration. Understanding these technical controls is fundamental to your role as a privacy technologist, as infrastructure vulnerability is a direct threat to personal data. By applying rigorous isolation and continuous monitoring, you minimize the blast radius of potential incidents. Remember that the code you write to manage your cloud environments is just as important as the code that processes raw data. As you move forward, keep the principle of least privilege in mind, applying it to your network routing tables just as strictly as you would to your database access tokens. Consistency in these deployments is the only way to achieve repeatable security success at scale. I will see you in the next lecture. Hello, and welcome to this deep dive into the technical orchestration of incident response. In this chapter, we explore how to transition from reactive manual handling to automated resilient architectures designed to safeguard personal data during active security events. Building a robust incident response capability requires moving beyond basic ticketing systems toward a state of programmatic maturity where technical controls trigger automatically upon the detection of an anomaly. When we talk about incident response in a privacy-centric context, our primary objective is to execute rapid containment to prevent unauthorized exfiltrations of personal data from escalating into a full breach. This necessitates the implementation of automated network isolation routines that can dynamically update firewall rules or VLAN tagging the moment a service begins exhibiting unusual traffic patterns. By decoupling a compromised node from the wider production network via software-defined networking APIs, you effectively create a digital quarantine zone without needing human intervention to physically pull cables. These routines must be idempotent and tested frequently to ensure they do not accidentally cause mass denial of service for legitimate users during a false positive scenario. The goal is surgical precision and isolation, relying on pre-configured triggers that identify mass egress flows which deviate from established baselines. Once containment is achieved, the focus must immediately shift toward automated database locking mechanisms and forensic preservation workflows to ensure the integrity of the evidence. When a database cluster detects unauthorized access patterns consistent with mass scraping or SQL injection, the system should be capable of programmatically escalating authentication requirements or entering a read-only state for specific sensitive schemas. This action needs to be coupled with an instant forensic preservation process that creates a point-in-time snapshot of the database volumes and captures current volatile memory states across the affected application nodes. In a cloud-native infrastructure, this is typically handled by invoking snapshotting APIs for storage buckets and persistent disk blocks, ensuring that the state of the data at the exact moment of discovery remains immutable for later analysis. Without this automated orchestration, the time required for manual forensic capture often leads to the corruption or overriding of crucial evidence logs necessary for root cause identification. By automating the creation of these forensic artifacts, we ensure that auditors and incident responders can conduct a post-mortem review with high confidence in the data integrity. Effective detection hinges on building automated alerting systems that monitor system telemetry with a specific focus on identifying unauthorized mass data exfiltrations in real time. We achieve this by instrumenting our application and network layers to export high-fidelity flow details, which are then fed into a centralized logging pipeline that evaluates traffic volume against expected operational norms. When an alert triggers, it must do more than simply notify a human operator. It should enrich the context by pulling details from identity management services to verify whether the offending sessions correspond to authorized service accounts or potentially compromised user credentials. The ingestion of these system logs for forensic purposes should include raw network flow details and API request traces, as these are the primary breadcrumbs that allow us to reconstruct the attacker's progression through our environment. To make this data actionable, engineers should architect dashboards that unify log streams from disparate components into a singular view. By streamlining these views, we can significantly accelerate the response time, which is critical when facing the clock on mandatory regulatory notification windows that often require reporting within mere hours of discovery. The culmination of this architectural effort is the ability to map incident data directly to regulatory notification requirements, turning a chaotic operational crisis into a structured reporting exercise. Regulatory frameworks across the globe impose increasingly stringent timelines on organizations to report privacy breaches, and any manual delay in assessing the scale of impacted personal data can lead to significant non-compliance penalties. By maintaining a well-documented data lineage and linking our automated responses to data classification metadata, Our incident dashboard can provide immediate visibility into exactly which datasets were touched by a specific breach. This allows privacy officers to bypass the tedious manual reconciliation of logs and move straight to calculating the risk and volume of affected data subjects. Furthermore, keeping forensic logs in a forensically sound state, meaning they are cryptographically signed, timestamped, and stored in write-once read-many storage, serves as the primary defensive evidence during subsequent audits or legal inquiries. Ultimately, your incident response architecture acts as a safety net that enforces privacy commitments even when things go wrong. I will see you in the next lecture. Hello, and welcome back to our deep dive into the technical intricacies of web privacy. Today, we turn our attention toward the fundamental mechanics of state management in the browser. HTTP cookies have evolved from simple session tokens into complex objects that dictate how data persists across user sessions. Understanding their architecture is not just about functionality, but about managing the privacy surface area of an application. When we set a cookie, we are effectively delegating trust to the browser to maintain that state on behalf of our server. If you configure these attributes without careful consideration, you expose your users to significant risks, primarily session hijacking and cross-site request forgery. A robust implementation requires balancing the need for persistent state with the imperative to restrict the scope and accessibility of data storage. We must treat every attribute as a security control rather than a mere setting. The foundation of modern cookie security lies in the flag-based configuration that governs how browsers handle data transfers. The HTTP-only flag remains our primary defense against cross-site scripting attacks, as it prevents client-side scripts from accessing sensitive tokens via the document. Posh Cookie API. When you omit this flag, you implicitly allow any script running in the security context of your page to read the cookie, which is a significant vulnerability. Similarly, the secure flag ensures that the browser will only transmit the cookie over encrypted HTTPS connections. Without this, sensitive session identifiers are vulnerable to man-in-the-middle interception on insecure networks. These two attributes should be considered the mandatory baseline for any cookie intended to carry authentication data. The same-site attribute is perhaps the most critical evolution in recent years for mitigating cross-site request forgery. By setting same-site to strict, the browser prevents the cookie from being sent in any cross-site request, which ensures the highest level of protection but can negatively impact user experience. If users arrive at your site from an external link, they will appear unauthenticated because their session cookie is withheld. A more pragmatic, yet still secure, choice is the lax value, which allows the cookie to be sent during top-level navigation initiated by a safe HTTP method like GET. The none value, typically required for legitimate cross-site functionality, forces the developer to also implement the secure flag, effectively mandating HTTPS for all third-party integrations. Beyond traditional cookies, modern web applications rely on browser-based storage architectures like local storage, session storage, and IndexedDB. These mechanisms offer larger storage capacities, but fundamentally change how we manage the privacy lifecycle of data. Unlike cookies, these storage areas do not automatically send data to the server with every request, but they are fully accessible to client-side JavaScript. This makes them inherently more susceptible to XSS-based data exfiltration because there is no equivalent to the HTTP-only flag for local storage or IndexedDB. When you store information in these formats, you must implement rigorous sanitization pipelines and content security policies to restrict where your scripts can send data. Choosing the right storage medium often means preferring cookies for critical state and using local storage for transient, non-sensitive UI preferences. Recent shifts in browser enforcement have introduced partition cookies and strict domain scoping as a primary response to aggressive third-party tracking. Partition cookies, or chips, allow developers to opt into a model where cookies are bound to the top-level site that sets them, isolating their influence across different domains. This prevents a third-party provider from correlating user behavior across the entire web. When designing your architecture, you should always define the domain and path attributes to be as restrictive as possible. A cookie scope to the entire domain is far more dangerous than one scope to a specific subdirectory. By enforcing the principle of least privilege in your scope definitions, You drastically reduce the damage potential if a specific service within your monolithic application is compromised. Engineering for privacy means acknowledging that every state management decision is a trade-off. We must constantly evaluate the balance between the functional requirements of our feature set and the data footprint we leave on the client machine. As browser vendors continue to tighten restrictions on third-party tracking mechanisms, the technical implementation details will grow in importance. You should view the secure, HTTP-only, and same-site attributes as an integrated contract with the browser's security sandbox. If we neglect these technical requirements, we are essentially failing to build the essential privacy safeguards that our users expect and that regulations require today. Mastery of these browser primitives is not optional for the modern privacy technologist. It is the core of our daily practice. See you in the next lecture. Hello, and welcome back to our deep dive into the technical landscape of modern privacy. Today, we are exploring the mechanics of tracking technologies that operate silently within the browser environment. To understand persistent identification, we must look beyond traditional cookies and examine how modern web beacons and tracking pixels function. A tracking pixel is typically a transparent one-by-one GIF embedded within a web page, which triggers an HTTP request when loaded by the client. This request sends the user's IP address, browser metadata, and the referring URL to a third-party server. Because the execution happens client-side, the browser acts as a conduit that automatically transmits telemetry to advertiser domains without the user ever interacting with these elements. While cookies are stored locally and can be deleted by the user, these server-side logs on the third-party platform correlate these requests to build a long-term behavioral profile. As a privacy technologist, you should recognize that these pathways rely on the standard way browsers handle resource loading, making them incredibly difficult to block without disrupting functionality. Browser fingerprinting takes this passive tracking approach to a significantly higher technical level by querying hardware and software configurations. Instead of relying on stored identifiers, scripts can probe the Canvas rendering API to determine how specific fonts, graphics, and anti-aliasing settings are rendered on a machine. Because different GPUs and driver versions produce microscopic differences in these renders, the resulting hash acts as a unique digital signature for that specific device. Additionally, scripts can query the WebGL context, the list of installed media devices, and even audio stack configurations to add further entropy to the fingerprint. This process does not require traditional storage access, meaning it persists even in private browsing modes or when third-party cookies are completely disabled. From an engineering perspective, this represents a significant shift from state-based tracking to heuristic-based identification. Analyzing these behaviors requires a rigorous approach to inspecting network requests and script execution patterns within your own applications. When auditing, you should observe the outgoing traffic to see which third-party domains receive sensitive data payloads during common user-side events. Many analytics platforms embed scripts that use complex obfuscation techniques, making it difficult to immediately identify what information is being extracted. Use browser development tools to examine the call stack when scripts query sensitive APIs like media devices or hardware context. By monitoring the frequency and destination of these calls, you can begin to map the data lineage of your own front-end services. Automated script analysis tools can assist in this by flagging dependencies that invoke restricted APIs, allowing you to intercept these calls before they leave the client's browser. Implementing defensive posture against unauthorized tracing is a core responsibility for the privacy-aware developer. You can mitigate these risks by configuring robust content security policies that restrict which domains are allowed to load resources or send tracking telemetry. By defining strict source directives for scripts and images, you effectively disable the unauthorized pathways that trackers use to reach external ad networks. Corporate web applications should also undergo periodic asset reviews to ensure that no third-party libraries have been silently updated to include new profiling capabilities. Treating dependencies as external entities with high surface risk allows you to audit the impact of analytics platforms on user privacy consistently. Developing these automated checks into your standard deployment pipeline ensures that your application remains aligned with data minimization goals throughout its lifecycle. See you in the next session. Welcome back to our exploration of modern privacy engineering. In this session, we will examine the technical architecture required to implement consent frameworks effectively. Integrating a consent management platform, or CMP, into a production environment is rarely as simple as pasting a snippet of JavaScript into the header of your website. From an engineering perspective, the core challenge lies in the orchestration of conditional script loading and the reliable propagation of intent throughout your entire distributed system. You must treat consent signals not as static flags, but as dynamic data points that dictate the state machine of your front-end application. When a user interacts with a banner, the browser must immediately store that intent locally while simultaneously initiating an asynchronous communication to your backend infrastructure. The goal is to ensure that no tracking pixels, analytics beacons, or third-party advertising scripts execute before the user has made an affirmative choice. This requires a defensive coding strategy where your tag manager acts as a gatekeeper for all outgoing data streams. To build a robust integration, you should interface with industry standards like the Interactive Advertising Bureau Transparency and Consent Framework, which defines a standardized way to communicate user choices across the ad tech ecosystem. The framework uses a binary string, often called a TC string, which encodes binary representations of consent for specific purposes and vendors. Your architecture needs to interpret this string on both the client side and the server side to maintain consistency. On the front end, your tag manager must be configured with triggers that wait for a consent initialized event before firing any marketing tags. If you fail to implement this handshake correctly, you risk leaking user data, such as IP addresses or unique device identifiers, before a legitimate opt-in is recorded. This is technically equivalent to a race condition where the data collection process wins against the privacy control mechanism. Managing consent at scale requires more than just client-side logic. It necessitates a backend system that can ingest and store these records immutably. When a user changes their preference, your API endpoint should receive this update, timestamp it, and secure it within a database that allows for perfect auditability. I recommend using a cryptographically signed structure for each consent record, which includes the user's identity, the specific version of the privacy policy they accepted, and the exact timestamp of their choice. By signing these records with a private key, you create an unforgeable proof of consent that is vital for demonstrating compliance during a regulatory audit or incident response scenario. These endpoints must be idempotent and highly available, as downstream services will frequently query these states to determine whether to process a piece of user data. Once the backend is capturing this data, you need a mechanism to broadcast these real-time consent states to your various application components or microservices. You might consider propagating the consent status through JWT claims or a shared cache layer like Redis, ensuring that your backend services perform a real-time check before accessing sensitive data stores. For example, if your personalization service attempts to access a profile database, it should first verify the user's current consent scope by invoking a helper function that checks the latest valid record in your consent database. If the consent has been withdrawn or is insufficient for that specific processing purpose, the service must proactively mask or exclude that user's record from the output. Architecture of this nature moves privacy from a policy document into the actual execution path of your software, which is the hallmark of sophisticated privacy engineering. Implementing this logic demands a significant shift in how we handle tracking tags, necessitating a move toward modular, gated execution. Instead of static script bundles, consider a setup where your front-end components are injected dynamically based on the verified signal stored in the browser's persistent storage. If a user denies tracking, your system should degrade gracefully, serving content without the burden of non-essential data collection scripts. This approach satisfies the principle of privacy by design, by ensuring that the application environment effectively shrinks its attack surface in direct proportion to the user's articulated privacy requirements. It does mean more complexity in the build pipeline and a need for rigorous testing to ensure that the consent logic does not inadvertently block essential functional features. However, the resulting resilience against data leakage and compliance risk makes this investment in architectural discipline entirely worthwhile. I will see you in the next lecture. Hello, and welcome back. In this lesson, we are going to explore the mechanics behind browser controls like global privacy control and do not track. In the landscape of modern web privacy, Browser signals serve as the primary intent mechanism for users expressing their data preferences before an interaction even fully matures. As engineers, our responsibility is to ensure that these signals are not merely ignored, but are actively ingested by the server-side architecture. When a browser sends a global privacy control signal, it is effectively declaring that the user wishes to opt out of the sale or sharing of their personal information. This is communicated through a specific HTTP header, SEC GPC, which your web application must be prepared to intercept at the earliest possible stage of the request lifecycle. By placing this detection logic within your load balancer, API gateway, or middleware, you ensure that the privacy preference is established before the request reaches the business logic layer. If you ignore this check, you risk trailing state where user data might be processed or shared despite an explicit, machine-readable objection. While modern protocols like global privacy control have replaced much of the original Do Not Track initiative, the technical implementation patterns remain conceptually similar. The D&T header, expressed as a simple key-value pair, requires your application to evaluate the visitor's intent while simultaneously balancing it against local regulatory requirements. An engineer must map these incoming headers to persistent operational data switches that govern downstream marketing automation systems. For instance, if your backend receives a signal, the corresponding user session object should be flagged immediately to prevent the ingestion of behavioral data into your ingestion pipelines. This mapping is not a passive task. It requires a robust middleware component that sanitizes the outbound data flow based on this signal. Relying on client-side JavaScript alone is a dangerous mistake, because a user can disable scripts or manipulate the browser environment to bypass local enforcement. When we shift our focus to client-side handlers, we must ensure that our JavaScript implementation acts as a secondary verification point rather than a primary gatekeeper. While server-side headers are the source of truth, client-side logic is useful for dynamically adjusting the rendering behavior of the page, such as disabling tracking pixels or blocking third-party initialization scripts. Developers should structure their initial load phase to check for navigator.global privacy control properties immediately upon execution. If the property exists and is set to true, the application should conditionally load authorized scripts only. This approach creates a two-tiered defense system where the server handles data handling logic, and the client manages the visual and behavioral footprint. Maintaining this separation of concerns is vital for auditability and compliance reporting across your web estate. Technical requirements for adjusting application rendering and database logging profiles revolve around the concept of functional decomposition. Your database logging layer should receive a context object that includes the current privacy signal state, ensuring that if a user has opted out, their activity is either not logged or is stripped of identifiable attributes. This is often where many implementations fail because developers forget to propagate the signal context through the call stack. A well-designed system uses a unified request context that is injected into every service, ensuring that even if a request hits 3 different microservices, the opt-out signal remains effectively tethered to the transaction. Automating this propagation ensures that your privacy posture is consistent across the entire distributed architecture. If you cannot guarantee that the signal follows the data, you cannot fulfill the technical obligations required by modern privacy regulations. Testing these configurations requires more than just manual browser verification. You need automated scripts that simulate various user agent configurations to ensure compliant behavior. You should build integration tests that inject specific headers into your staging environment and assert that the subsequent database records do not contain protected information. These tests should cover edge cases where headers might be malformed or inconsistently provided across different browsers and versions. By baking these checks into your continuous integration pipeline, you move privacy from a manual process toward a verifiable engineering dependency. An automated verification script is the only way to prove to auditors, and to your own peace of mind, that you are respecting browser signals at scale. Always assume that your manual checks will fail eventually, and that rigorous, code-based verification is the only path to architectural integrity. I will see you in the next lecture. Welcome back. We are now turning our technical focus towards the unique privacy landscape of mobile application environments. In this lecture, we will explore the specific constraints and requirements inherent in building privacy-compliant native applications. Modern mobile ecosystems operate under a strict sandbox architecture that fundamentally dictates how data is accessed and shared. On iOS, the App Tracking Transparency Framework requires explicit user authorization before an application can access the advertising identifier or share data across other companies' apps and websites. Android takes a similar approach through the Privacy Sandbox, which aims to phase out persistent third-party tracking identifiers in favor of aggregated and cohort-based signals. As a privacy-focused engineer, you need to treat these platform-level APIs as the primary gatekeepers of user consent. When you configure your SDKs, you're not merely implementing a feature, you are configuring the interface between your application's telemetry needs and the operating system's privacy enforcement mechanisms. Managing identification on these platforms requires a departure from legacy tracking methods that relied on hardware identifiers. Historically, developers leaned on the Apple IDFA and the Google Advertising ID to stitch together user profiles across various ecosystem silos. Today, relying on these identifiers without strict observance of ATT prompts or Google's evolving privacy guidelines will likely result in App Store rejection or, worse, significant regulatory friction. Instead, move toward ephemeral, session-based identifiers that exist only within your primary application context. When you must facilitate advertising, ensure your implementation utilizes the official platform-provided APIs that request consent at the appropriate runtime moment, rather than attempting to bypass these controls through background fingerprinting, which is explicitly prohibited by mobile distribution policies. The storage layer on mobile devices presents its own set of privacy challenges that demand robust engineering patterns. Every mobile operating system provides a sandboxed file system, but simply relying on default permissions is rarely sufficient for sensitive information. You must implement file system-level encryption where the keys are derived from secure hardware enclaves like the iOS keychain or the Android key store. When data remains at rest within your local database, ensure that your encryption implementation uses strong, industry-standard algorithms, such as AES 256, for all PII-related fields. By isolating data within an encrypted container, you add a critical layer of defense that protects user information even in scenarios where the device security is compromised or the underlying file system permissions are misconfigured. Telemetry logging often creates an unintended privacy leak when developers inadvertently include sensitive data in raw diagnostic streams. If your application sends logs to a backend aggregator, you should adopt zero-knowledge telemetry practices by scrubbing or hashing PII before the data ever leaves the mobile endpoint. Implementing a local proxy layer can help you intercept and validate all background data transmissions before they reach your network edge. This practice enables you to maintain a strict whitelist of outgoing traffic, ensuring that third-party SDKs, which are often the silent culprits of excessive data harvesting, do not unilaterally transmit user activity data behind your back. Rigorous validation of these dependencies is not optional when you operate in a high-privacy regulatory environment. Finally, the distribution marketplaces require transparency that must be baked into your build process from the inception. Both Apple and Google mandate nutritional label-style data disclosures that summarize exactly what your application collects and how that information is utilized across the lifecycle of the user interaction. Automating the generation of these manifests directly from your codebase ensures that your public-facing privacy claims are always synchronized with your actual data collection behavior. By treating these disclosure requirements as part of your schema definition rather than a post-development afterthought, you create a verifiable trail of accountability. This proactive approach significantly lowers the risk of non-compliance and builds long-term user trust within your mobile ecosystem. I will see you in the next lecture. Welcome back. In this session, we will examine the privacy implications of API telemetry and how to secure these channels against unauthorized data harvesting. API telemetry serves as the nervous system of modern distributed applications, providing essential visibility into performance, usage patterns, and potential security threats. However, when these telemetry streams are poorly configured, they transform from diagnostic tools into vectors for data leakage, specifically regarding sensitive user information. An API endpoint often inadvertently broadcasts more metadata than required for basic monitoring, which invites reverse engineering and automated scraping attempts. To defend against such threats, you must implement strict rate-limiting policies that go beyond standard global thresholds. Utilizing a token bucket algorithm is a robust choice here, as it allows for bursts of traffic while firmly enforcing a sustained throughput limit that deters high-volume automated harvesting bots. By aligning your rate limiting with specific user or device context, you effectively neutralize the utility of brute force scraping tools that struggle to mimic authentic, low-frequency human interaction patterns. Beyond rate control, securing the authenticity of the data being transmitted is paramount for preventing man-in-the-middle manipulation and unauthorized request injection. Cryptographic request signing acts as a digital seal, ensuring that the payload received by your gateway has not been tampered with and originated from an authorized client. When your infrastructure validates these signatures at the edge, you establish a primary line of defense that rejects unauthorized traffic before it can even reach your core application logic or internal tracking systems. Dynamic behavior analysis tools complement this by building a baseline of normal interaction, allowing you to trigger automated responses when a client deviates into anomalous patterns. For instance, if a device starts querying unique IDs across the entire system range in a linear fashion, your gateway filters should be configured to flag and terminate that session immediately. This proactive stance is essential when dealing with bulk data access, as it limits the surface area exposed to bad actors at any single point in time. Telemetry pipelines often feed into third-party analytics integrations, which introduces the significant risk of PII sprawl across external environments. You must ensure that every payload destined for these platforms undergoes a strict filtering process directly on the client side or via a middleware scrubber. It is a common mistake to send an entire object to an analytics service when only a specific performance metric is required. Yet this single action can leak PII like email addresses or persistent device identifiers. You need to enforce data mapping at the API gateway level to intercept these payloads and explicitly strip out any unauthorized fields before they transit to third-party endpoints. This is not just a security preference, but a functional requirement for compliance, as the liability for how that third party handles the data remains partially with the originating organization. By treating every telemetry packet as a potential privacy incident, you maintain a tighter control over your data footprint and limit the impact of a potential breach in your analytics chain. Effective defense also requires that your automated integration tests treat API boundary security as a first-class citizen. You should write test suites that specifically attempt to pulse check the telemetry endpoints by sending malformed payloads or anomalous requests to ensure the gateway blocks them as expected. These tests act as a continuous feedback loop that validates your filtering logic every time code is deployed to production. When your developers know that a build will fail if they accidentally expose a new field in an API telemetry snapshot, they naturally gravitate toward more conservative and privacy-centric coding practices. This integration of DevSecOps into your telemetry lifecycle transforms the abstract concept of data minimization into a concrete, measurable technical reality. By validating the refusal of bulk PII requests through these automated boundary tests, you guarantee that your defenses remain effective even as your system architecture evolves over time. See you in the next lecture. Welcome to our exploration of artificial intelligence through the lens of privacy engineering. We will cover the risks associated with machine learning architectures and how to implement technical controls to mitigate them. In this chapter, you will master the essential techniques required to secure modern machine learning pipelines, including large language models and deep neural networks. We are going to deconstruct the systemic privacy risks inherent in automated training cycles and investigate how to build robust defenses against data leakage. By the end of this curriculum, you will possess the specialized knowledge required to implement machine unlearning, data curation filters, and secure inference environments that meet the highest privacy standards. If you want to position yourself as a leader in technical privacy, this chapter provides the rigorous, evidence-based tools you need to succeed. Machine learning models, particularly large language models, present a unique privacy challenge because they often exhibit a tendency to memorize training data. This memorization is a systemic risk because it allows an adversary to perform membership inference attacks, where they determine if a specific data record was part of the training set. Furthermore, model inversion attacks can potentially reconstruct sensitive features of the training data by querying the model repeatedly and observing the output distributions. To mitigate these risks, you must shift your focus toward data curation and input-output sanitization before data ever touches the training pipeline. It is not enough to rely on the model's internal complexity to hide privacy-sensitive information. You must proactively filter the dataset to ensure no personal identifiers are present in the final vector embeddings. The concept of machine unlearning is gaining traction as a necessary component of lifecycle management for neural networks. When a user exercises their right to be forgotten, you cannot simply perform a database delete operation because the information might be baked into the weights of the model. Machine unlearning algorithms allow for the selective removal of a data subject's influence from a model without the massive computational expense of retraining from scratch. This process usually involves calculating the influence of specific training points on the model's loss function and performing a targeted gradient update to erase that influence. You should consider these techniques as non-negotiable requirements when deploying deep learning models in environments subjected to strict regulatory audits. When deploying models into production, the inference environment itself becomes a significant attack vector that requires a layer of obfuscation or sanitization. If your model accepts user prompts, you are essentially handling raw, uncurated input that could potentially be logged or used to retrain future model iterations. I recommend wrapping your model endpoints in a secure gateway that applies input-output sanitization to prevent the injection of malicious queries and to ensure that generated outputs do not divulge restricted data. Furthermore, you must implement strict logical isolation for secondary data reuse loops, ensuring that production prompts are not automatically cycled back into a dataset for training unless they undergo a rigorous anonymization process. These architectural decisions define whether your implementation is truly private by design or merely compliant on the surface. Auditing training datasets is a fundamental phase of a privacy-conscious machine learning lifecycle that often gets overlooked in favor of model performance metrics. You should treat your training data as a high-risk asset that needs its own inventory and classification mapping, similar to how you treat production databases. This involves running automated data curation filters that scan for patterns resembling personal identifiers, such as social security numbers, emails, or biometric markers before the training cycle initiates. By creating a lineage that tracks where these data points originated and whether they were transformed, you maintain the ability to satisfy compliance requests even after the data has been ingested into a high-dimensional feature space. Technical auditors will look for this trail, and having it ready is a sign of a mature privacy engineering organization. See you in the next lecture. Welcome to our exploration of biometric infrastructure, where we examine how to architect secure systems for processing sensitive physiological data. In this chapter, we will focus on the technical mechanisms required to protect biometric templates throughout their entire lifecycle. When we handle biometric data, we must move beyond the naive assumption that we are storing images or recordings of a person. Instead, we are dealing with mathematical abstractions that represent unique physiological features. The first step in any robust biometric infrastructure is the transformation process. We take raw input, such as a fingerprint scan or iris feature set, and apply algorithms to generate a biometric mathematical vector. This vector is not a photo. It is a point in a multidimensional mathematical space. To ensure privacy, this process must be non-reversible. We should treat these vectors as cryptographic assets from the moment of generation. By hashing these templates using salted, one-way functions, we ensure that even if a database were compromised, an attacker could not reconstruct the original physiological features. This mathematical transformation is the bedrock of non-reversibility in modern privacy engineering. Centralized databases of biometric templates represent a significant honeypot for attackers. To mitigate this risk, we shift our perspective toward decentralized verification models. In a decentralized architecture, we authenticate the user locally on their device, rather than streaming raw biometric data to a centralized server. The device holds the template, and the matching process occurs within a secure enclave or a trusted execution environment. Only the result of the verification, typically a signed token confirming a successful match, is transmitted to the server. This design pattern aligns perfectly with the principle of data minimization because the server never sees the raw biometric template. If the central infrastructure suffers an intrusion, the attacker gains no usable biometric data, as the actual templates remain distributed across individual endpoints. Defense in depth is the only reliable strategy when dealing with biometric spoofing and replay attacks. We must assume that an attacker will attempt to present a fake fingerprint, a 3D printed face, or a high-quality recording to bypass authentication. To counter this, we implement liveness detection, which requires the system to verify that the biometric sample is coming from a living, present human being. This involves multimodal sensors that verify physical characteristics like pulse, thermal signatures, or micro-movements of the skin. Beyond liveness detection, we must protect against replay injections where a malicious actor intercepts a valid, previously captured success token and attempts to replay it. Implementing a time-bound, cryptographically signed nonce ensures that any token used for verification is uniquely linked to that specific authentication event. Protecting the pipeline from capture to verification is a continuous battle against evolving adversarial techniques. The life cycle of biometric data ends with secure destruction. We must move away from the misconception that simply deleting a database row removes the data. Because biometric data can be persisted in logs, backups, cache files, or memory dumps, we need formal, automated routines to purge these assets. Secure deletion must be cryptographically sound, meaning we should delete the key used to encrypt the template if we are managing our secrets correctly. Once the key is destroyed, the data becomes effectively inaccessible, fulfilling our regulatory obligations for data erasure. These routines need to be part of the system design from the start, rather than an afterthought bolted on during an audit. Properly implemented lifecycle management ensures that when a user revokes consent or a template expires, the data is truly gone. See you in the next lecture. Welcome to our exploration of the Internet of Things, where we will examine how to secure constraint-driven ecosystems against modern privacy threats. We will focus on implementing robust architectural patterns that prioritize data minimization and secure hardware management. The Internet of Things introduces a unique set of constraints that traditional security models struggle to address because many edge devices operate with limited processing power, minimal memory, and low bandwidth. When we talk about securing these ecosystems, we must move away from the assumption that every node can support full-scale transport layer security or heavy asymmetric encryption suites. Instead, we need to consider lightweight cryptographic protocols, such as elliptic curve cryptography, which provides a high degree of security with smaller key sizes compared to traditional RSA methods. Secure boot operations are equally foundational here, as they establish a chain of trust from the hardware level up to the operating system, ensuring that only cryptographically signed firmware can execute on a device. Without this mechanism, a malicious actor could intercept the update stream, inject unauthorized code, and gain persistent access to the sensor data stream. By hardening the boot process, we create a resilient foundation that prevents compromised nodes from becoming permanent gateways for external threats or unauthorized data collection loops. Data collection within these distributed environments presents a significant privacy risk if left unmitigated, as raw sensor telemetry often contains personally identifiable indicators or behavioral patterns that can be traced back to a specific individual. A more effective architectural approach is to move the processing logic to the edge, where we can filter, aggregate, and normalize data before it ever touches a central repository. By anonymizing raw sensor input directly on the hardware, we ensure that the information transmitted across the network is already stripped of identifying context, which significantly reduces the impact of potential wireless eavesdropping. We should design our pipelines to implement data suppression, where only the delta changes or statistical summaries are sent, rather than continuous streams of high-resolution data. This not only improves bandwidth efficiency, but also limits the inherent privacy exposure that comes with constant network chatter. If you're building an edge processing architecture, always remember that local aggregation acts as a powerful privacy boundary between the device and the cloud, effectively neutralizing many pervasive tracking vectors. Managing the life cycle of these devices requires a disciplined approach to onboarding and maintenance, particularly when considering how credentials or identifiers are handled. Secure device onboarding should involve unique, hardware-backed identities that are provisioned during manufacturing, rather than relying on global default passwords or static certificates that could be leaked at scale. Once deployed, automated firmware update systems become the primary lever for security, though they must be designed with remote credential revocation capabilities to handle nodes that are physically or logically compromised. We must also address the issue of network-level identifiers, as hardware MAC addresses are static and can easily serve as persistent tracking beacons for anyone monitoring local wireless signals. To mitigate this, we should configure edge devices to perform dynamic randomized MAC address rotations, which makes it significantly harder for adversaries to correlate long-term activity with a single physical unit. Establishing these automated patterns ensures that our privacy posture remains consistent across thousands of devices without individual manual oversight, which is simply not feasible in large-scale deployments. When we integrate these components effectively, we move from a reactive security posture to a proactive design strategy that respects the privacy of the end user at every layer of the hardware stack. It is important to treat every node as a potentially hostile environment where physical tampering is always a possibility, forcing us to rely on encryption at rest and in transit. By enforcing strict telemetry streaming pipelines that only acknowledge cryptographically verified endpoints, we prevent rogue devices from joining the network and spoofing authentic data. This level of rigor might seem taxing during the initial phase of system design, but it is the only way to ensure that our decentralized infrastructure does not become a liability for the organization. As we continue, keep in mind that the constraints of the hardware are not necessarily limitations on your work, but rather design parameters that guide you toward a more efficient and private architecture. Building these safeguards directly into the firmware and protocol handling ensures that privacy is not an afterthought, but a core functional requirement of the ecosystem. See you in the next lecture. Welcome to our exploration of cloud implementations, where we will examine the technical requirements for maintaining privacy in massive, multi-tenant environments. Cloud environments operate on a shared responsibility model, which often leads to complex configuration gaps if not managed with clinical precision. When we discuss AWS, Azure, or Google Cloud Platform, the primary concern is the logical isolation of data and compute resources through landing zones. A landing zone serves as the architectural foundation of your cloud footprint, establishing the governance guardrails, network topology, and identity boundaries necessary for compliance. By utilizing services like AWS organizations or Azure management groups, you define management boundaries that prevent unauthorized cross-account access. You must treat these management boundaries as non-negotiable security perimeters that dictate how data flows between different business units or isolated cloud accounts. Regional resource location constraints are equally vital because data sovereignty regulations frequently mandate that PII and other sensitive records remain within specific geographic jurisdictions. If your infrastructure spans multiple global regions, you must enforce policy-based controls that prevent the deployment of storage buckets or relational databases in unauthorized regions. Setting these regional guardrails at the governance layer ensures that human error cannot accidentally move data outside of a compliant territory. Once your boundaries are established, the next challenge is ensuring that your configuration does not drift over time as your cloud footprint scales. This is where automated serverless governance scripts become a necessity rather than a luxury for responsible engineering teams. You can construct functions that trigger on specific events, such as the creation of an S3 bucket or a blob container, to verify that public access blocks are correctly enabled. If a script detects a storage volume without the appropriate encryption settings or restrictive access control lists, it should automatically trigger a remediation event. I prefer designing these as stateless functions that operate on an event-driven basis, allowing for a continuous, low-latency audit of your entire storage estate. By programmatically asserting a known good state for your configuration, you shift privacy from a manual review process to an inherent property of the system architecture. This proactive stance is essential when dealing with thousands of ephemeral resources that developers might spin up without deep knowledge of privacy by design requirements. Beyond general configuration, you must address the technical realities of detecting and containing sensitive information within cloud-native object stores. Most major cloud providers offer built-in data loss prevention services that use machine learning to scan for patterns like credit card numbers or government IDs. When you deploy these tools, you are essentially setting up a continuous surveillance layer that monitors every object upload. The configuration requires you to define inspection templates that map exactly what constitutes PII within your specific operational context. Once the DLP tool identifies unencrypted sensitive data in an object store, it can trigger immediate actions, such as isolating the object or alerting your security operations center. This is a critical technical control for organizations that rely on large-scale data lakes where manual auditing is physically impossible due to the sheer volume of files. Implementing these controls correctly requires constant testing to tune your sensitivity thresholds and avoid excessive false positives that could hinder production workflows. Finally, we must turn our attention to the necessity of visibility through unified cloud logging pipelines. Privacy engineering is rarely effective if you lack a comprehensive trail of access, particularly in multi-account environments where infrastructure configurations change by the second. You should aggregate logs from identity management services, resource configuration changes, and object access requests into a centralized, immutable storage location. This logging pipeline acts as the single source of truth for your internal and external audits, proving that you maintain oversight over who accesses your systems. It is not sufficient to simply store these logs. You must derive actionable insights from them through automated alerting on anomalous access patterns. By monitoring for unusual cross-account activity, you can detect a potential data breach or a misconfigured identity policy in near real time. This level of granular visibility ties together your identity management, secure configuration, and data protection efforts into a cohesive technical fabric. Your primary goal is to ensure that privacy compliance is a verifiable, automated, and observable state of your entire cloud infrastructure. I will see you in the next lecture. Welcome to our exploration of distributed ledger technologies and the inherent privacy tensions they create. We will examine how to reconcile the permanence of blockchain with the legal necessity of data erasure. Distributed ledger technology, or DLT, presents a fundamental architectural challenge to privacy engineering because these systems are designed for immutability. When we record data on a public or even a private permission blockchain, that record is effectively permanent and irreversible by design. This conflicts directly with statutory requirements found in regulations like the GDPR, which grant individuals the right to erasure or the right to be forgotten. In a traditional database environment, we can simply execute a delete command on a specific row to satisfy a data subject request. In a distributed ledger, however, the consensus mechanism relies on the integrity of every previous block, making the removal of a record mathematically impossible without breaking the chain. This is not merely a technical limitation, but a systemic conflict between decentralization and the regulatory mandate for control over one's personal data. To mitigate these structural privacy challenges, we must adopt an off-chain storage design pattern. Instead of writing PII or sensitive personal records directly into a ledger transaction, we should store that sensitive data in a secure, centralized, or distributed relational database. We then generate a cryptographic hash of that data and store only that hash within the immutable ledger. When we need to verify the data at a later date, we compare the current data against the stored hash to ensure it has not been tampered with. If a user exercises their right to erasure, we simply delete the original record from the off-chain database. Because the ledger only contains the hash and not the actual personal information, the ledger remains technically compliant, even if the hash can no longer be resolved to a specific user record. The key to making this model work is effective key management, specifically regarding what is often called cryptographic shredding. If we encrypt the off-chain data before storing it, the data becomes effectively inaccessible if we destroy the decryption keys. By deleting the unique encryption key associated with a specific user's off-chain records, we essentially fulfill the mandate of data erasure even if the encrypted blobs remain technically present on disk. This is a common pattern in cloud storage, and it is highly applicable here as a way to maintain the integrity of decentralized systems. We must ensure that the mapping between users and their specific encryption keys is tightly controlled and auditable, as the loss of these keys equates to permanent data destruction. Effectively, the key replaces the record, and destroying the key is the functional equivalent of shredding the data itself. Zero-knowledge proofs, or ZKPs, offer a more sophisticated approach for when we need to validate transactions without ever exposing the underlying user data. A ZKP allows one party to prove to another that a statement is true. such as confirming a user is over the age of 18 without revealing the user's actual date of birth or any other identifying information. By leveraging ZKPs, we can perform complex verification of states, such as account balances or identity attributes, entirely on-chain. This keeps the ledger clean of raw PII while still enabling the decentralized trust that serves as the core utility of blockchain technology. Implementing ZKPs reduces the attack surface significantly, as there is never a single source of personal truth that can be breached or leaked from the network. In architecting systems that touch distributed ledgers, you must perform a thorough privacy impact assessment centered on data lineage and persistence. Consider the scenario of a supply chain platform using blockchain to track pharmaceutical provenance. Every node holder technically possesses a copy of the ledger, which expands the perimeter of risk significantly. If that ledger contains even pseudonymous identifiers that can be linked back to a person through correlation, you have created a permanent privacy leak that cannot be patched. Your task is to insist on architectural minimalism by restricting the information written to the ledger to the absolute minimum necessary for the protocol to function. Every field you add to a ledger transaction is a liability that will live on indefinitely. So evaluate every byte for the risk it introduces to the data subject. Security professionals must also account for the fact that distributed ledgers are often public or shared across organizational boundaries, which complicates the definition of a data controller. If you are operating on a public chain, you may lack the ability to effectively control the data processing environment, which raises significant compliance hurdles. Always evaluate whether the ledger technology is truly necessary for the business goal, or if a traditional controlled database would provide the same outcome with less privacy risk. Privacy engineering is about matching the right tool to the mandate, and DLT is often chosen for buzzwords rather than technical necessity. By applying these strategies, you can build systems that leverage the transparency of distributed ledgers without compromising the fundamental rights of the individuals whose data they technically represent. I will see you in the next lecture. Hello, and welcome to this session regarding the intersection of quantum computing and information security. We're going to explore how quantum advancements threaten current cryptographic standards. When we discuss the security of data in transit or at rest, we implicitly rely on the computational hardness of specific mathematical problems. Current public key infrastructure, or PKI, is built upon the assumption that factoring large integers or computing discrete logarithms is computationally infeasible for classical computers. RSA relies on the difficulty of prime factorization, while elliptic curve cryptography, known as ECC, exploits the difficulty of the elliptic curve discrete logarithm problem. These systems are pervasive in protecting everything from TLS connections to encrypted database volumes, effectively forming the bedrock of modern digital privacy. However, the theoretical development of Shor's algorithm changes this landscape significantly, as it provides a polynomial time solution for these specific mathematical tasks. If a sufficiently powerful fault-tolerant quantum computer were to be constructed, these foundational cryptographic systems would effectively be rendered obsolete overnight. Shor's algorithm functions by utilizing quantum superposition and interference to find the period of a function, which directly translates into solving those factoring and logarithmic problems that classical machines find intractable. While today's noisy, intermediate-scale quantum devices are not yet capable of executing this algorithm at a scale that breaks RSA 2048, the risk is not purely speculative. We operate in an environment defined by the store now, decrypt later paradigm, where threat actors harvest encrypted traffic today with the intention of exposing it once quantum capabilities mature. This reality forces us to evaluate the shelf life of the sensitive data we manage, particularly when that data requires protection for decades. If you are designing a system today that must maintain confidentiality for 20 years, you are already vulnerable to an adversary who can capture current traffic and decrypt it in the future. Consequently, we must shift our perspective from immediate hardening to long-term architectural resilience against these future capabilities. To mitigate these threats, the industry is moving toward post-quantum cryptography, often referred to as PQC, which consists of cryptographic algorithms designed to withstand quantum cryptanalysis. NIST has been spearheading the standardization of these algorithms, focusing heavily on lattice-based structures that rely on the shortest vector problem in a high-dimensional lattice. Unlike prime factorization, finding the shortest vector in an as-efficiently high-dimensional lattice is believed to be computationally difficult even for quantum computers. Algorithms such as Crystal's Keeper and Crystal's dilithium are being integrated into libraries intended to replace classical variants. Because these algorithms operate with different performance characteristics and key sizes, simply swapping out an RSA implementation for a lattice-based one is rarely a trivial exercise. Engineers must carefully consider the impact of these changes on latency, memory consumption, and network throughput within their existing software stacks. The recommended strategy for bridging the gap between classical systems and a quantum-resistant future involves the configuration of hybrid cryptographic layers. In a hybrid approach, data is wrapped in two layers of encryption, one using a established classical algorithm and the second using a PQC algorithm. This provides a safety net because if one algorithm is found to be flawed or broken, the other still provides a layer of security. This methodology is particularly relevant for transport layer protocols, where we can negotiate dual key exchanges to protect session secrets. When considering data at rest, we must also audit our storage volumes to identify where legacy encryption is deeply coupled with application logic. Migration plans should prioritize the modularization of cryptographic providers, allowing for the agile replacement of underlying primitives without necessitating complete rewrites of the data layer or the business logic. Moving toward a quantum-ready architecture requires a methodical approach that mirrors our established routines for security updates and patching. You should begin by performing a cryptographic inventory to identify where public key operations are utilized throughout your enterprise. Once you have a clear map of these dependencies, you can start testing PQC-ready modules in staging environments to observe their performance impact. Do not assume that moving to quantum-resistant standards will be an automated process executed by your vendor. Instead, prepare your team by incorporating crypto agility into your system design principles. This involves abstracting cryptographic operations away from the application code, which allows you to update algorithms at a configuration level as standard bodies publish new guidance. We are effectively preparing for a structural upgrade to the internet, and early planning is the only reliable defense against the inevitable obsolescence of our current security assets. I will see you in the next lecture. Welcome back. In this chapter, we explore the technical architecture required to fulfill Data Subject Access Requests, or DSARs, effectively and securely. Building a system to handle high-volume DSARs requires moving away from manual, spreadsheet-based processes toward fully automated, reproducible workflows. When you view these requests as an engineering problem, you realize the core challenge is data discovery across a distributed architecture. You need to implement search indices or metadata catalogs that map unique identifiers, such as an email address or a customer ID, across your entire storage landscape. It is not enough to simply query a primary relational database. You must account for semi-structured logs, object storage, and potentially third-party SaaS caches where user data might reside. Automating these extraction engines involves writing robust scripts that can iterate through various endpoints without creating significant performance degradation in your production environment. You are effectively building an internal search engine that must respect the sensitivity of the data it retrieves during the harvest phase. Once you have aggregated the data, the next critical step is ensuring that the package you deliver remains strictly limited to the requesting individual. One common pitfall is the accidental inclusion of third-party personal information within the extracted dataset. If you are retrieving a chat transcript or a collaborative document, the extraction engine must recognize and redact PII belonging to other users before completion. This typically involves deploying natural language processing libraries or regex-based pattern matching that scans the payload for identifiers like credit card numbers, tax IDs, or other contact information. You should view this as a sanitization pipeline where input data is cleansed based on predefined privacy policies. By enforcing these rules at the transformation layer, you ensure that the machine-readable JSON output is both compliant and safe for the end user to receive. Verification and secure delivery are the final and perhaps most sensitive components of the fulfillment technical stack. You cannot simply email a link to a file, as this creates a new vector for data leakage if the recipient's identity is not verified or the transport channel is insecure. The preferred architecture involves a gated portal where, after multi-factor authentication, the user receives a time-limited, encrypted download token. Use industry-standard encryption protocols, such as AES-256 for the data at rest in your storage bucket, and ensure that TLS 1.3 is enforced for the connection itself. Logging every stage of this lifecycle is also a requirement, as it provides an audit trail showing when the request was received, what data was extracted, and when the user ultimately accessed the download link. By treating the DSAR pipeline with the same security rigor as your general access control systems, you mitigate the risk of a fulfillment request becoming a source of a new privacy incident. Consider the structure of your data models when designing these automated retrieval systems to support portability. If a data subject requests their data in a machine-readable format, JSON is generally the standard, but the internal schema map is what really drives the efficiency of the software. You need to maintain a clear relationship between the subject's identity and the data attributes stored in different microservices. If your architecture is highly fragmented, you might look into implementing a data broker pattern where a central service orchestrates the requests to various downstream systems. This decoupling allows you to update your storage backend without needing to rewrite the entirety of your DSAR fulfillment logic. Maintainability is just as important as security, as privacy regulations evolve, and the definition of what constitutes personal data changes over time. Finally, prioritize the scalability of your extraction engines during periods of high demand. If you have a large user base, a mass request event could potentially overload your database infrastructure if not properly rate limited. Design your background workers to process extraction tasks asynchronously, perhaps through a task queue system that operates in the background to ensure that production user experience remains unaffected. Avoid synchronous calls to heterogeneous data stores, as a single slow response from a legacy system could block the entire request workflow. Instead, prioritize reliability by implementing circuit breakers and monitoring the health of your discovery services constantly. Delivering a seamless, automated experience creates trust and demonstrates to regulators that your firm holds privacy engineering as a top-tier operational priority. I will see you in the next lecture. Welcome to this chapter on automated operations, where we will focus specifically on the technical execution of data erasure. In this lesson, we will explore the engineering requirements for building robust pipelines that handle the right to be forgotten at scale. When we approach the challenge of automated erasure, we must shift our perspective from manual, reactive processes to proactive, programmatic orchestration. In a modern distributed architecture, sensitive data rarely resides in a single database. It is typically replicated across caching layers, analytical data warehouses, and log aggregators. If a user exercises their right to erasure, simply issuing a delete command to a primary SQL server is insufficient. We need a system that treats the deletion request as a transactional event that propagates through the entire ecosystem. The most effective way to achieve this is through a message-driven architecture where a consumer listens for a unique deletion token. Once the system receives this signal, it triggers a chain reaction that ensures the identifier is scrubbed from all downstream services, maintaining strict consistency across the infrastructure. Building these pipelines requires careful consideration of how our different storage layers handle data persistence. In relational databases, we might perform a hard delete, but if that table uses indexes, we must account for the overhead of index rebuilding routines that prevent performance degradation or residual data remnants. When we move to object storage, we often transition from active records to delayed purge configurations, which requires an orchestration layer that handles object lifecycle policies. Caching layers present their own unique challenges because they are ephemeral by design and often lack the metadata necessary to honor targeted deletions. To bridge this gap, we implement invalidation logic that prevents the serveback of stale, sensitive data after the primary record has been destroyed. The most complex architectural hurdle involves immutable systems like write, once-read mini backup archives or log aggregators, where deletion is physically impossible or prohibited by audit requirements. Here, we must reach for cryptographic erasure as our primary mechanism for compliance. By wrapping individual user datasets or tenant records with unique data encryption keys, we can effectively render that data unrecoverable without needing to rewrite the actual backup media. The process involves keeping a meticulous mapping of these keys, and upon an erasure request, we delete the specific key, not the encrypted data. This key shredding ensures that the underlying bits remain on the disk or tape in an encrypted state that is mathematically impossible to decrypt, satisfying the regulatory definition of destruction. Beyond the technical implementation, we are obligated to prove that our automated pipelines are functioning as expected through strict verification routines. It is not enough to send a success signal back to the client. We need an asynchronous feedback loop that monitors system state after the erasure triggering event. We can achieve this by implementing periodic reconciliation jobs that compare a list of active users against the records present in our disparate storage systems. If a system report indicates that an identifier was not successfully purged from an analytical cluster or a secondary backup copy, the orchestration layer must generate an alert for immediate remediation. This creates a defensive, self-healing architecture that minimizes the risk of human error in compliance workflows. This holistic approach to data erasure transforms compliance from a burdensome legal requirement into a standard engineering capability. By integrating these processes deep into the back-end infrastructure, we reduce the total time to fulfillment and decrease the surface area for manual data handling mistakes. We ensure that our systems remain compliant by design rather than by manual intervention, which is the hallmark of a mature privacy engineering organization. We must always strive to minimize technical debt while ensuring that we satisfy the legal constraints placed upon our data stores. By mastering these patterns, you will be well equipped to manage the lifecycle of personal data within complex, high-velocity environments. I will catch you in the next lesson. Welcome to this session on integrating privacy directly into your operational workflows. We will explore how to transition from reactive privacy compliance to a proactive model built directly into your deployment pipelines. Embedding automated privacy compliance into your CI/CD pipelines moves the burden of verification left, closer to the source of code changes. Instead of relying on periodic manual audits, we can treat privacy requirements as executable code, often referred to as policy as code. By integrating frameworks like Open Policy Agent or similar engine-based validators, you can inspect infrastructure as code templates for misconfigurations before they reach production. For instance, an automated scanner might inspect a Terraform script to verify that database encryption is enabled and that public access to storage buckets is explicitly disabled by default. If a developer attempts to commit code that relaxes these privacy-enhancing controls, the build pipeline identifies the violation, triggers an alert, and rejects the deployment. This feedback loop ensures that privacy-preserving configurations are maintained throughout the entire software development lifecycle rather than being an afterthought. Container security also serves as a critical pillar in this integrated automated architecture. Every time a new container image is pushed to your registry, your CI/CD engine should trigger an automated scan for known vulnerabilities and hard-coded secrets. If a container references outdated libraries with known privacy flaws or contains sensitive API keys, the process should automatically block the rollout to the live environment. Beyond static analysis, we must also consider the dynamic nature of our test environments where developers often work. Using raw, identifiable user data for testing is essentially a privacy failure. So we must automate the provisioning of isolated test environments that utilize synthetic or masked datasets. By script loading these sanitized datasets, we decouple development agility from the risks associated with processing real user information, ensuring that security and privacy never come at the cost of technical progress. Monitoring and alerting provide the final layer of this operational privacy framework by observing the system after it is live and functioning. You should configure your infrastructure to report on privacy-specific metrics, such as unexpected data egress patterns or unauthorized access attempts to PII-containing services. When your observability platform, perhaps Prometheus or an ELK stack, detects an anomaly that violates a predefined privacy threshold, it can automatically trigger an incident response workflow or alert a privacy engineer. This creates a closed-loop system where privacy thresholds are not just theoretical documents, but live, enforced technical boundaries. If a microservice begins interacting with a database in an unapproved manner, the automated alerting loop isolates that component to prevent a large-scale privacy breach. This continuous monitoring is the hallmark of a mature DevSecOps practice, where privacy visibility is as accessible as system uptime or CPU load. See you in the next lecture. Welcome back to this exploration of privacy engineering. Today, we turn our attention to the technical auditing chapter, where we will translate abstract policy requirements into tangible, automated verification processes within your production environments. In the domain of modern software engineering, reliance on manual checklists is a recipe for failure because configurations drift and systems evolve at a pace that humans cannot track on their own. Technical auditing is the systematic approach to validating that your privacy controls are not only architected correctly, but are also functioning as intended within the live infrastructure. Think of this as the equivalent of continuous integration for compliance, where we automate the verification of security and privacy states to ensure they match our documented, authorized configurations. When we talk about production environments, we are concerned with the actual state of databases, API configurations, and network traffic patterns, rather than the intent stated in a design document. By shifting from periodic, point-in-time assessments to automated, continuous auditing, we reduce the latency between a configuration drift and its remediation, which is essential for maintaining a verifiable privacy posture. To implement this effectively, we must start by configuring automated tools that interrogate our database permissions and transmission configurations at regular intervals. A core requirement is to verify that encryption in transit is enforced across all service endpoints and that static data at rest satisfies our defined encryption standards. Automation scripts can be written to pull the active state of database access control lists and compare them against a baseline configuration file stored in your version control system. If a developer inadvertently grants excessive permissions or switches off a TLS requirement on a service gateway, the auditor flags this deviation immediately for investigation. This process is not merely about identifying errors, but about creating a feedback loop where the infrastructure itself provides proof of compliance. By defining what constitutes the authorized state as code, we can continuously poll our infrastructure to detect unauthorized drift before it manifests as a regulatory incident. Beyond basic connectivity checks, we must also audit the application logic that enforces data minimization and retention policies. Custom scripts can simulate user deletion requests or data expiration events to ensure that data is purged or redacted according to the configured retention timelines. For example, if a policy dictates that user metadata must be removed after 90 days, a technical audit script should periodically query the database for records exceeding that timestamp to confirm they are indeed being processed for deletion. This validation requires deep integration with your data storage layers and, specifically, the mechanisms responsible for lifecycle management. By quantifying the number of records that successfully move through the deletion lifecycle versus those that might be orphaned due to logic bugs, you generate the concrete evidence needed for external reporting. These reproducible trails demonstrate to regulatory bodies that your privacy controls possess an operating health that is monitored, measured, and verified continuously. The final piece of this puzzle is the centralization of these findings into a reporting dashboard that transforms raw technical data into meaningful privacy metrics. Relying on disparate log files scattered across various servers makes it nearly impossible to provide an audit trail during a regulatory inquiry. By streaming audit results into a centralized logging platform, we create a unified view of the privacy infrastructure's status, allowing us to generate health reports formatted for non-technical stakeholders. These dashboards should reflect the health of encryption, the accuracy of access controls, and the efficacy of data minimization efforts. When an auditor asks for evidence that a specific control was active on a certain date, your centralized logs provide a reliable, immutable, and time-stamped history of that control state. Developing these observability pipelines is as much a part of privacy engineering as implementing the controls themselves, because a control that cannot be audited is, for all practical purposes, a control that does not exist. See you in the next lecture. Welcome back. We are now turning our technical focus towards the critical domain of vendor assessment within privacy operations. In this session, we will examine how to maintain control over data integrity when third-party services are integrated into your architecture. When we integrate third-party APIs or software development kits, We are essentially extending our organizational security boundary to include entities outside of our direct governance. The central challenge lies in the fact that vendors frequently update their own code bases, which can inadvertently lead to unauthorized data leakage or changes in how they process information. To mitigate this risk, you must transition from static contract reviews to active, continuous technical monitoring of the data payloads that travel to these external endpoints. By writing custom script validation routines, you can inspect the serialization of outgoing objects before they leave your environment. This practice ensures that sensitive user attributes are not being transmitted unless they are strictly required for the service to function, effectively creating a technical guardrail against vendor overreach. Building automated testing sandboxes is a highly effective, albeit underutilized, method for evaluating the hidden behaviors of third-party SDKs. You should instantiate these isolated environments to perform deep packet inspection and binary analysis on SDKs before they are permitted to reach production. Within these sandboxes, you are looking specifically for hidden telemetry signals, persistent background storage calls, and unexpected cross-site tracking markers. If an SDK contacts a third-party server that was not explicitly outlined in the vendor's technical documentation, your sandbox should automatically flag the anomaly. This proactive testing approach shifts the burden of proof onto the vendor, allowing your team to verify claims of compliance through empirical data rather than relying solely on vendor-supplied questionnaires. To enforce strict granular control, engineers must implement proxy layers that sit between your application core and the external vendor API. These proxies act as a mandatory inspection point where outbound data streams can be analyzed and, if necessary, sanitized according to predefined privacy policies. You can configure these proxies to perform schema validation, ensuring that only the specific fields authorized for disclosure are passed forward, while stripping out any incidental data that might have been caught in the request object. If a legitimate request contains an unapproved attribute, the proxy can either transform the payload by redacting the sensitive element or reject the request entirely until the application code is corrected. This mechanism provides a robust defense in depth strategy that prevents improper data exposure even when the application logic fails to perform its own filtering duties. Continuous observability depends on your ability to construct actionable data processing alerts that trigger whenever an API behavior deviates from your established baseline. Start by mapping all known user attributes to the specific vendor endpoints that are authorized to receive them. This creates a formal allow list. Any outbound API call that attempts to transmit an attribute outside of this list should trigger an immediate notification for your security engineering team. Furthermore, monitor for changes in the volume and frequency of data being sent, as a sudden spike in outgoing traffic may indicate that a vendor has quietly modified their collection practices. By correlating these technical alerts with your data inventory, you turn privacy compliance into a measurable, real-time engineering metric rather than a lagging indicator. See you in our next technical discussion. In this lesson, we explore the complexities of migrating legacy systems into modern, privacy-respecting architectures. We will examine the operational and engineering strategies required to refactor data structures while maintaining rigorous privacy compliance. Dealing with legacy systems is often the most significant hurdle in modernizing a privacy program. These systems were frequently built long before modern data protection regulations evolved, meaning they lack native support for privacy by design concepts like granular access control or automated data deletion. When we look at refactoring an old database schema, the primary challenge is not just the physical movement of data, but the implicit business logic tied to legacy, unencrypted schemas. Often these architectures rely on monolithic structures where data is stored in a single, deeply interconnected environment that lacks clear isolation boundaries. You must approach this by breaking down those monoliths into smaller, manageable service components that can enforce privacy tags uniformly across the data ecosystem. If you fail to create these isolation boundaries, you risk inheriting the security vulnerabilities of the past, thereby neutralizing the intent of your migration project. A robust migration path requires creating a parallel processing environment rather than attempting to modify the live production system directly. By spinning up a secondary architecture that mirror images the original, you establish a staging ground where you can validate the transformation of data under realistic constraints. You should develop extraction pipelines that map legacy fields to new privacy-compliant structures, ensuring that sensitive identifiers are pseudonymized or tokenized at the point of ingestion. This parallel approach allows for non-destructive testing, where you can run both systems in tandem to verify that the transformed data yields the same logical results. Only after you have validated the structural integrity and the application of correct privacy tags can you begin the controlled transition of traffic to the new environment. This process prevents the common pitfall of data loss during translation and gives you an explicit safety net if the reconciliation phase reveals inconsistencies. Validation and verification are the heartbeat of a successful migration strategy. Once your primary data flows are re-architected, you need to implement automated validation checks that compare the output of the legacy system against the newly structured data. These checks should look for anomalies in record counts, data formatting, and most importantly, the presence of proper privacy metadata. If you find that a field contains personal information that bypassed your encryption or anonymization requirements, your validation strategy should halt the migration trigger immediately. Relying on manual inspection here is a recipe for error. So invest in automated scripts that audit the data lineage from the legacy source to the new destination. This level of rigor ensures that the new system is not just functionally equivalent to the old one, but actually performs according to your current data protection impact assessment requirements. Fallback strategies must be designed into the very architecture of the migration plan to account for unforeseen outages or corruption events. You should establish a clear point of no return, where if the delta between legacy and new systems exceeds a predefined threshold, the system automatically reverts to the known good state. Beyond technical rollbacks, you must maintain exhaustive audit logs throughout the transition process to reconstruct events if something goes wrong. These logs serve a double purpose. They help you troubleshoot technical failures during the migration phase and provide the necessary documentation for potential regulatory inquiries. If you encounter a failure, your documentation should clearly distinguish between data transformation errors and infrastructure failures. This precision speeds up the recovery time and allows your team to address the specific root cause without needing to restart the entire data migration job. The final step in any migration is the secure decommissioning of hardware and data structures that are no longer in use. Data professionals often overlook this phase, leaving residual sensitive data on old drives that are then moved to secondary storage or discarded insecurely. You need to implement a formal, documented policy for purging retired nodes that includes cryptographic erasure and, when applicable, physical destruction of storage media. Every decommissioned system must be audited to ensure that no cached or replicated copies of sensitive legacy data remain in obscure backup locations. Eliminating the original access footprints effectively reduces your attack surface and ensures that your enterprise architecture complies with data minimization requirements. Following these steps systematically protects the organization from the long-term risk of data breaches stemming from obsolete and forgotten technology assets. I will see you in the next lecture. Welcome to the conclusion of our journey through the CIPT certification landscape. We have arrived at the final synthesis of the technical competencies required to lead privacy engineering initiatives effectively. To succeed in this examination, you must first consolidate your understanding of privacy engineering as a rigorous, structural discipline rather than a sporadic administrative task. We have walked through the entire data lifecycle, from the initial mapping and inventory creation to the final disposition of records, ensuring that every touchpoint respects the principle of data minimization by design. It is now imperative that you internalize those core patterns, such as the separation of sensitive datasets and the implementation of robust access controls, which form the bedrock of any defensible architecture. Remember that the certification board expects you to demonstrate not just knowledge of cryptographic primitives or obfuscation tactics, but an ability to articulate why specific privacy-enhancing technologies are appropriate for a given risk profile. Your technical fluency must bridge the gap between abstract policy requirements, like those found in the GDPR or CCPA, and concrete system implementations in modern distributed environments. If you can envision how an automated erasure workflow interacts with a legacy relational database while maintaining integrity, you are well positioned for success. Approach every scenario-based question by first identifying the data flow and the underlying regulatory obligation before selecting the technical control. When you encounter complex dilemmas, lean on the fundamental privacy design principles we discussed, as they provide the most consistent heuristic for navigating gray areas in technical implementation. Managing your time effectively during the exam requires a deliberate, methodical approach to reading and decoding the case studies presented. These multi-layered scenarios are designed to distract you with irrelevant operational details. So your primary task is to strip away the noise and isolate the core privacy engineering question. When you see a reference to third-party interactions or cross-border data transfers, immediately recall the framework application and vendor assessment criteria we explored in the earlier sections. Do not allow yourself to become anchored by a single challenging question. Instead, flag it, move forward, and draw upon the technical breadth we have covered to build your confidence through the questions you can answer readily. Throughout this course, we focused on building a coherent mental model that connects threat modeling with actual risk quantification. And this is exactly what you need to deploy during the test. Your ability to distinguish between anonymization and pseudonymization, particularly under the lens of re-identification risk, will be tested extensively. Keep your focus on the technical mechanisms for enforcing consent and technical auditing, as these are the verifiable evidence points that regulators and auditors seek. As you step into your professional role as a privacy technologist, recognize that the certification is merely the formal acknowledgement of a set of skills that must be applied continuously. Your mandate as an engineer is to embed privacy directly into the DevSecOps pipeline, moving away from reactive patching toward a proactive, built-in posture. The technical artifacts you produce, such as data maps and impact assessments, serve as living documents that must reflect the evolving state of your infrastructure, especially as you integrate emerging technologies like artificial intelligence or IoT devices. You are now equipped to navigate the tensions between business utility and data protection, providing clear, actionable guidance to stakeholders. Use the frameworks we have discussed to translate complex technical vulnerabilities into clear risk indicators that the executive team can understand and act upon. Trust in the foundational principles you have mastered. Maintain your commitment to rigorous system documentation and continue to refine your technical curiosity in this rapidly shifting field. By focusing on the structural integrity of your privacy controls, you demonstrate the professional maturity that characterizes a certified information privacy technologist. I am confident that you are ready to tackle the examination with the technical depth and professional rigor required to pass. See you in the next lecture.